Welcome to The Chill Scientist. The story of the Voyager probes begins long before their launches in 1977. It starts with a remarkable opportunity in celestial mechanics, one that happens only once every 176 years. In the late 1960s, a group of NASA engineers and scientists realized that the outer planets, Jupiter, Saturn, Uranus, and Neptune, would align in such a way during the late 1970s and 1980s that a single spacecraft could use their gravity to slingshot from one to the next, like a cosmic relay race. This technique, known as gravity assist, had been demonstrated in earlier missions like Mariner 10 at Venus, but never on such a scale. If timed precisely, a probe could gain momentum at Jupiter, redirect towards Saturn, then continue on to Uranus and Neptune, all without carrying massive amounts of fuel. It was an extraordinary chance to visit all 4 giant planets in one continuous mission, a grand tour of the outer solar system. The original vision for this grand tour was incredibly ambitious. NASA scientists proposed launching 4 spacecraft, 2 to fly past Jupiter, Saturn, and Pluto, and 2 to visit Jupiter, Uranus, and Neptune. Together, they would explore all the outer planets and several of their largest moons in a single sweep, revolutionizing planetary science. The concept was bold, but it came at a time when budgets were tightening and public enthusiasm for space exploration had cooled after the Apollo program. As the dream collided with reality, NASA was forced to scale back. Instead of 4 spacecraft, only 2 would be built, with missions officially designed to explore Jupiter and Saturn. Anything beyond that would be considered extended. This cautious approach kept costs down while still taking advantage of the rare planetary alignment. Even with a reduced scope, the project promised unprecedented science. At the time, knowledge of the outer planets was limited to fuzzy telescope images and a few flybys. Pioneer 10 and 11 had paved the way by crossing the asteroid belt and reaching Jupiter and Saturn in the early 1970s, but their instruments were limited, and their images, though groundbreaking, were crude compared to what was hoped for next. Voyager would take the baton from Pioneer, carrying more advanced cameras, spectrometers, plasma detectors, and magnetometers. The mission would not only photograph the planets and their moons in detail, but also measure their atmospheres, magnetic fields, radiation belts, and ring systems. It was a mission designed to rewrite textbooks, to transform outer planet science from sketches into detailed portraits. Behind the engineering, there was also a spirit of exploration driving the project. The late 1960s and early 1970s had seen humanity step onto the moon, but the outer solar system remained utterly uncharted. To most people, planets like Uranus and Neptune were little more than names in a textbook, faint points of light at the edge of sight. Voyager promised to change that. By bringing back close-up images and data, the mission would transform those points into worlds, strange, dynamic, and real. It was not only a scientific venture, but a cultural one, capturing the imagination of a generation hungry for discovery. The decision to pursue the Voyager mission came at a pivotal moment for NASA. After Apollo, the agency faced uncertainty about its long-term direction. The Space Shuttle program was still years away from its first launch, and there was pressure to justify costly planetary missions to a public less captivated by space than in the 1960s. Voyager represented a chance to deliver high-profile results without the cost of crude exploration. It was also a test of whether robotic spacecraft could be used for ambitious, long-duration missions, laying the groundwork for the planetary science program that continues today. The Voyager probes were not just about science, they were also about endurance. From the start, engineers designed them to last for years, not months. They would need to survive the harsh radiation belts of Jupiter, the icy darkness of the outer solar system, and the long communication delays that grew with each passing million kilometers. The probes had to be tough, reliable, and autonomous, capable of executing complex sequences without constant instructions from Earth. They would carry redundant systems, advanced fault protection software for the time, and a power supply designed to function for decades. Every part of their design reflected the enormity of their journey. As the mission concept took shape, excitement grew among scientists. The Grand Tour alignment would not happen again until well into the 22nd century. This was not just another mission, it was a once-in-a-lifetime chance. To miss it would mean waiting generations before trying again. In that sense, Voyager was born not only out of opportunity, but out of urgency. The planets would not wait. Either humanity would seize the chance in the late 1970s, or it would vanish into the deep rhythm of celestial mechanics. This urgency gave the mission an energy that would carry it through the decades to come. When the Voyager probes were first conceived, no one could have predicted just how long they would last or how far they would go. Officially, they were designed to fly past Jupiter and Saturn. In practice, they would go much farther, crossing into interstellar space and becoming the most distant human-made objects ever launched. But in those early years, as the Grand Tour alignment loomed, the focus was simple: build the spacecraft, launch them on time, and prepare for a journey that would change everything we knew about the outer solar system. The early 1970s were a time of both optimism and caution for space exploration. The Apollo missions had delivered astronauts to the moon, proving that humanity could reach another world, but the cost had been staggering. NASA now faced shrinking budgets and growing skepticism about its long-term role. Into this climate came the realization that the late 1970s offered a rare planetary alignment. Every 176 years, the outer planets arranged themselves in such a way that a spacecraft launched from Earth could visit them in sequence, using the gravitational fields of each to bend its path and boost its speed. This technique, gravity assist, allowed a probe to extend its mission without carrying huge amounts of fuel. The alignment was a gift of celestial mechanics, and if NASA did not act, the next chance would not come until well into the 2010s. The initial proposal was audacious. NASA scientists imagined a fleet of spacecraft, 4 in total, that would take advantage of this alignment. 2 would head toward Jupiter, Saturn, and Pluto, while the other 2 would continue on to Jupiter, Uranus, and Neptune. Together, the missions would explore every giant planet, several major moons, and even Pluto in a single sweep. It was nothing less than a complete tour of the solar system's outer reaches. The scientific payoff was immense. Close-up images, direct measurements of atmospheres and magnetospheres, and data on moons that were barely known. It was the ultimate planetary reconnaissance, the kind of mission that would define a generation of space science. But reality quickly set in. The cost of 4 spacecraft and the infrastructure to support them was far beyond what Congress was willing to fund. In the wake of Apollo, enthusiasm for billion-dollar planetary missions was low, and the appetite for high-risk exploration was limited. NASA was forced to scale back the concept, trimming the Grand Tour into something more modest. Instead of 4 spacecraft, there would be 2. Instead of promising to explore all 4 giant planets, the official mission would be limited to Jupiter and Saturn. If the spacecraft survived, they might continue farther, but that was considered an extended mission, not a guarantee. This more conservative design helped win approval for the program, but the scientists and engineers behind it never lost sight of the bigger goal. They knew that if the spacecraft were built to survive the journey to Jupiter and Saturn, they would also be capable of traveling to Uranus and Neptune. So in practice, they built the probes with durability and longevity in mind, hoping that when the time came, NASA would extend the mission. It was a gamble, but one rooted in optimism. The planetary alignment was too rare, too valuable, to treat as a simple 2-planet flyby. Even if the official paperwork called for only Saturn, the spacecraft were designed with Neptune in their future. Designing the mission in the early 1970s also meant considering how to send data back across billions of kilometers. The Deep Space Network, NASA's global array of radio antennas, would be crucial for maintaining contact. The farther the probes traveled, the weaker the signals would become. Engineers calculated that by the time Voyager reached Neptune, the power of its signal arriving at Earth would be measured in billionths of a billionth of a watt, barely distinguishable from background noise. Yet with massive antennas and careful data handling, they believed it could be done. This confidence in engineering was as much a part of the mission as the planetary science itself. The mission also had to plan for the timing of launches. To take advantage of the alignment, Voyager 2 would need to launch in August 1977, followed by Voyager 1 in September. Though Voyager 1 launched second, it would actually arrive at Jupiter first, because its trajectory was more direct and faster. This reversal in numbering sometimes confused the public, but it was a practical decision made to ensure that both spacecraft could reach their targets with the best trajectories. Timing was everything. A launch window missed by even a few weeks could mean losing the chance for the entire planetary tour. The choice of instruments was equally critical. Cameras capable of photographing planets and moons in unprecedented detail were included, along with spectrometers to measure atmospheric composition, magnetometers to map magnetic fields, and detectors for plasma, particles, and cosmic rays. Each instrument represented a piece of the puzzle, chosen to answer key questions about the outer planets. What were their atmospheres made of? How strong were their magnetic fields? Did they have rings, like Saturn, or moons yet unseen? Voyager would provide the answers. By the time the mission entered final planning, excitement was growing among scientists worldwide. The prospect of seeing Uranus and Neptune up close for the first time was irresistible. These planets were little more than dots in telescopes, their disks blurred and their moons invisible. To fly past them, to capture their true faces, would transform planetary science forever. It was the closest thing to exploration in the old sense, voyaging into the unknown, unsure of what would be found. In many ways, the planning phase of Voyager captured the very spirit of exploration that had driven sailors across oceans centuries before. The early 1970s planning thus set the stage for one of humanity's greatest scientific adventures. Though constrained by budgets and politics, the mission team managed to preserve the core of the grand tour, ensuring that Voyager would be capable of more than its official goals. With the launch window approaching, the spacecraft themselves began to take shape, each one a marvel of engineering designed to travel billions of kilometers, survive for decades, and send back a stream of data that would rewrite our understanding of the solar system. The opportunity of a lifetime was within reach, and NASA was determined not to miss it. Building the Voyager spacecraft was an exercise in balancing ambition with pragmatism. The probes had to travel farther than any spacecraft before them, survive longer than most engineers dared hope, and carry a suite of instruments sophisticated enough to reveal the mysteries of the outer planets. At the same time, budgets were tight, weight limits strict, and the environment of deep space utterly unforgiving. Every decision made in the design process reflected this tension between what scientists dreamed of and what engineers could reliably deliver. The basic shape of Voyager was dictated by necessity. At its heart was a 10-foot wide high-gain antenna, a white dish that looked like an oversized satellite dish, which would serve as the spacecraft's voice across the solar system. Behind the dish sat the spacecraft bus, a framework holding computers, instruments, and subsystems. Extending outward were long booms carrying magnetometers, plasma detectors, and other sensitive equipment that needed to be kept away from the electronics to avoid interference. Another boom held the power source. 3 radioisotope thermoelectric generators, or RTGs, that converted the heat of decaying plutonium into electricity. Solar panels were not an option at the distances Voyager would travel. Sunlight was simply too weak. The choice of RTGs was controversial but essential. Each one provided about 160 watts of power at launch. slowly declining as the plutonium decayed. Engineers knew that by the time Voyager reached Neptune in the late 1980s, the power available would be a fraction of what it had been at Jupiter. This meant careful power management would be critical. Instruments could not all be run at once. Heating would have to be rationed. Redundancy was built in, but so was austerity. Voyager was designed to do a great deal with very little, stretching every watt as far as possible. Computing power was another area where Voyager's design reflected the era. The spacecraft carried 3 main computer systems, each with backup units. They handled command, attitude control, and sequencing. By today's standards, their capacity was laughably small. The memory of each was measured in kilobytes, not gigabytes, yet they were robust, radiation-hardened, and programmable from Earth. This last feature was crucial. No one could know in advance exactly what would be required during the planetary encounters. Voyager would need to be reprogrammed mid-flight, with new sequences uploaded across billions of kilometers. Flexibility was baked into the design. The scientific payload was a collection of carefully chosen instruments. There were 2 television cameras, one wide-angle and one narrow-angle, to capture both sweeping views and fine details. A photopolarimeter would study atmospheres and rings by measuring the polarization of light. A magnetometer would map magnetic fields, while plasma and particle detectors would study the charged environment around planets. An infrared spectrometer would analyze heat signatures, and an ultraviolet spectrometer would probe atmospheric composition. Together, these instruments gave Voyager a balanced set of eyes and ears, capable of studying everything from planetary weather systems to the faint trickle of cosmic rays from beyond the solar system. Designers also had to think about longevity in ways no spacecraft builder had considered before. Voyager might operate for more than a decade, crossing distances that would take signals hours to traverse. Mechanical systems had to be protected against wear. Lubricants had to function in extreme cold, and electronics had to resist radiation. The spacecraft would have to survive not just the deep freeze of space, but also the intense particle environments of Jupiter and Saturn, which could fry unprotected circuitry. Engineers layered shielding, tested components to destruction, and built backups wherever possible. It was insurance against the unknown. Communication was another challenge. At launch, Voyager would be only a few light minutes away, but by the time it reached Neptune, radio signals would take more than 4 hours to arrive. The Deep Space Network, with its massive 70-meter antennas in California, Spain, and Australia, would be Voyager's lifeline. Every bit of data the spacecraft returned had to be squeezed into the narrow bandwidth available, transmitted at painfully slow rates compared to modern internet speeds. A single high-resolution image could take hours to downlink. This limitation forced scientists to prioritize carefully. When the flybys came, they would have only one chance to capture the best data, and then weeks to trickle it home. The spacecraft also carried a human touch in the form of the Golden Record. Conceived by Carl Sagan and his colleagues, it was a phonograph record containing sounds, music, and images from Earth, intended as a message to any extraterrestrial intelligence that might one day encounter Voyager, drifting among the stars. The record was housed in a protective case, with instructions etched into it for how to play it, and mounted on the side of the spacecraft. Though not essential to the mission, it symbolized Voyager's dual role, both as a scientific explorer and as a cultural ambassador from humanity. It was a gesture that looked beyond the solar system to the galaxy beyond. As construction progressed, Voyager took shape not as a fragile experiment, but as a hardy emissary built to endure. Every nut, bolt, and circuit reflected thousands of hours of thought. Engineers tested the spacecraft in vacuum chambers, blasted it with radiation, and vibrated it to simulate the violence of launch. Failures were studied and corrected. Redundancy was added where possible, and compromises made where necessary. The result was a spacecraft that, while modest by some measures, embodied the best of 1970s engineering: durable, adaptable, and quietly elegant. By the mid-1970s, both spacecraft were ready. Identical twins, Voyager 1 and Voyager 2, each weighed about 1,800 pounds and carried the same suite of instruments. They were not flashy, nor were they perfect, but they were built with one overriding purpose: to survive the long journey into the outer solar system and return knowledge that would reshape our view of the planets. Few suspected just how long they would last or how far they would go. In the minds of most, a decade of operation would be a triumph. Anything beyond that would be a bonus. In retrospect, the choices made during the design of Voyager proved remarkably wise. The spacecraft would go on to endure for decades, far outlasting their expected lifespans, and continue to send back data even as their power supplies dwindled. They were not just spacecraft, they were time machines of a kind, built with the technology of the 1970s, but destined to survive into the 21st century and beyond. In their sturdy frames and limited computers lay the promise of discovery, carried farther than anyone in the 1970s could have imagined. The launch of the Voyager probes in 1977 was the beginning of one of humanity's most extraordinary journeys. Planning the mission required not only building the spacecraft, but also timing the launches to take advantage of a rare planetary alignment. Every 176 years, the outer planets line up in such a way that a single spacecraft can use gravitational assists to slingshot from one planet to the next, saving fuel and shortening travel time. This opportunity would not come again until well into the 22nd century, so missing it was not an option. Voyager 2 was launched first, on August 20th, 1977, atop a Titan IIe Centaur rocket from Cape Canaveral. Voyager 1 followed on September 5th, 1977. Though Voyager 2 left Earth earlier, Voyager 1's trajectory was faster, allowing it to overtake its twin and reach Jupiter and Saturn first. This naming quirk, Voyager 1 arriving before Voyager 2, was intentional and reflected the priority of its path. Voyager 1 was aimed for a close pass by Titan, Saturn's largest moon, while Voyager 2 was set on a more flexible route that could extend to Uranus and Neptune if all went well. The launches themselves were powerful, but relatively routine compared to the enormity of what came after. Once freed from Earth's gravity, the spacecraft entered the vastness of space with speeds exceeding 17 kilometers per second, about 38,000 miles per hour. This was fast enough to eventually escape the sun's gravity entirely, but for now, their paths curved toward Jupiter, the first and largest stop on their itinerary. The travel time to Jupiter would be nearly 2 years, a long cruise in the emptiness of space where engineering discipline and patience were tested. Early in the journey, controllers at NASA's Jet Propulsion Laboratory in California worked to commission the spacecraft. Instruments were powered on and tested, antennas adjusted, and the attitude control system fine-tuned to keep the high-gain antenna pointed back at Earth. The booms carrying the magnetometers were deployed, and the radioisotope power systems settled into their slow, steady output. There were hiccups, of course, false alarms, minor glitches, and the need to recalibrate systems, but nothing catastrophic. Both spacecraft were performing within expectations, quietly slipping deeper into the solar system. As they traveled, Voyager began collecting data even in interplanetary space. The magnetometers measured the solar wind, a stream of charged particles flowing outward from the sun. Plasma detectors picked up fluctuations in this wind, while cosmic ray instruments monitored high-energy particles from beyond the solar system. This background science helped establish a baseline of the heliosphere, the bubble of solar influence that surrounds the planets. Though not as headline-grabbing as the planetary encounters to come, these measurements were valuable in their own right, offering early insights into the dynamics of space weather. A key challenge during this phase was communications. Even at a fraction of their eventual distance, the Voyagers were already stretching the limits of the deep space network. Engineers had to carefully schedule antenna time, not just for Voyager, but for other missions as well. since the network served multiple spacecraft. Data rates were slow, often only a few bits per second when bandwidth had to be shared. Commands had to be timed precisely, with the knowledge that any mistake could take hours to correct due to the signal delay. The patience and meticulous planning of mission controllers became a hallmark of Voyager operations. This period also allowed for rehearsal of the flyby sequences that would come at Jupiter. The computers on board Voyager had to execute complex series of commands with minimal intervention, since the spacecraft would pass each planet in just a matter of hours. Engineers uploaded test sequences, watched the results, and refined their methods. Every photo and measurement during the flybys would have to be choreographed in advance. The spacecraft had no autonomy in the modern sense. It could only do what it was told, step by step, with no opportunity for improvisation once the moment arrived. One of the earliest tests of the imaging system came in 1979, when Voyager 1 captured its first long-distance photos of Jupiter. The giant planet appeared as a faint, growing disk, slowly sharpening over the months. For scientists, these early glimpses were tantalizing, a reminder of what awaited. Each new frame marked progress not just in distance, but in human anticipation. The cruise phase also highlighted the difference between the two spacecraft. Voyager 1's path was more tightly focused on its encounters with Jupiter and Saturn, aiming directly for Titan. Voyager 2's trajectory was deliberately designed with flexibility. If Voyager 1 succeeded, Voyager 2 would continue onward to Uranus and Neptune. If Voyager 1 failed, Voyager 2 would divert to ensure at least one spacecraft completed the Titan mission. This dual strategy reflected both caution and ambition, maximizing the odds of success while keeping the door open to even greater exploration. By the end of 1978, the spacecraft were firmly en route, and anticipation for the Jupiter encounters grew. Scientists began refining their predictions, planning which features to study and how to make the most of the brief flyby windows. The world, too, began to take notice. Though space exploration was no longer new, the scale of Voyager's journey captured imaginations. These were not just satellites in Earth orbit or probes to the moon. They were emissaries to the giant planets, carrying the promise of discovery on a scale never before attempted. The journey outward was calm compared to the storms they would soon witness, but it was essential. It gave engineers time to fine-tune their instruments, scientists time to prepare, and the spacecraft time to prove themselves reliable. By the time Jupiter loomed large in their cameras, Voyager had already achieved something remarkable. It had survived the long trek through interplanetary space, working exactly as intended, ready to reveal a new world in unprecedented detail. When Voyager 1 reached Jupiter in early 1979, it marked the first major payoff of the mission. After nearly 2 years of silent travel through space, the spacecraft approached the largest planet in the solar system, and for the first time, humans were about to see it with a clarity no telescope on Earth could provide. The encounter was not a single event, but a carefully orchestrated series of observations, beginning months before the closest approach and continuing well after, as Voyager sped past. The first thing that struck scientists as the images came in was the sheer complexity of Jupiter's atmosphere. From Earth, even the largest telescopes could only hint at the planet's bands and the famous Great Red Spot. Voyager's cameras revealed these features in exquisite detail, showing a planet alive with storms, swirls, and turbulence on a colossal scale. The Great Red Spot, larger than Earth itself, was revealed to be a vast anticyclonic storm with complex patterns of smaller vortices embedded within it. Surrounding it were endless cloud bands, shifting and colliding in ways that suggested a dynamic and chaotic atmosphere. Voyager also captured the colors of Jupiter's clouds with startling vibrancy. Shades of brown, red, white, and orange, all caused by chemical compounds in the atmosphere. Scientists debated what molecules were responsible, with suggestions ranging from ammonia and methane derivatives to sulfur compounds. Regardless of the exact chemistry, the images made clear that Jupiter was not a simple gas giant, but a world of intricate processes and immense energy. One of the most surprising discoveries came from the study of lightning and auroras. Instruments detected radio signals and bursts of energy that indicated Jupiter's atmosphere was crackling with lightning strikes, some far more powerful than those on Earth. Meanwhile, its auroras, glowing displays of light at the poles caused by charged particles interacting with the magnetic field, were revealed to be even more intense than those on our planet, a reflection of Jupiter's powerful magnetosphere. As Voyager drew closer, attention turned to the planet's moons. Before the mission, only a handful of details were known about the Galilean satellites, Io, Europa, Ganymede, and Callisto. They were assumed to be cold, cratered worlds, much like our moon. Voyager shattered that assumption almost immediately. Io, the innermost of the four, stunned scientists with evidence of active volcanism. Its surface was covered not in craters, but in bizarre plains, calderas, and flows. Voyager's cameras caught plumes erupting in real time, spewing material hundreds of kilometers above the surface. This was the first discovery of active volcanism beyond Earth, and it completely changed how scientists thought about planetary activity. Tidal forces from Jupiter's immense gravity, flexing Io's interior as it orbited, were identified as the source of the heat driving these eruptions. Europa, though less dramatic on the surface, was no less intriguing. Instead of craters, it was covered in smooth ice plains, etched with long cracks and ridges. This hinted at a young, active surface that could conceal a liquid ocean beneath. For the first time, scientists began to imagine the possibility of an ocean world beyond Earth, one that might harbor conditions suitable for life. Ganymede, the largest moon in the solar system, revealed a complex surface of mixed terrains. Some regions were heavily cratered, while others showed grooves and ridges, evidence of tectonic processes. It was not a dead world, but one shaped by internal forces, though less extreme than Io or Europa. Callisto, by contrast, appeared more ancient and heavily cratered, its battered surface suggesting it had changed little for billions of years. Beyond the Galilean moons, Voyager found a surprise: faint, narrow rings encircling Jupiter. Before the mission, no one knew Jupiter had rings at all. Though not as prominent as Saturn's, these rings added another layer to the planet's already impressive system and hinted that ring structures might be more common in the solar system than previously thought. The encounter also provided the first close-up measurements of Jupiter's immense magnetic field. Voyager's instruments revealed a magnetosphere extending millions of kilometers into space, dwarfing Earth's. Charged particles trapped in this field created harsh radiation belts, more intense than expected, which battered the spacecraft's instruments. This environment explained why Jupiter's auroras were so strong and why any future spacecraft would need careful shielding to survive near the planet. The data from Voyager 1's Jupiter flyby poured in steadily, despite the limited bandwidth of the time. Scientists pored over each image and graph, often working around the clock as new discoveries rolled in. The world's media followed closely, publishing stunning images of a planet and moons that seemed stranger and more alive than anyone had imagined. The sense of wonder was palpable. Humanity was seeing these worlds for the first time, and they were nothing like the barren, cratered spheres most had expected. By the time Voyager 1 swung past the planet and headed for Saturn, the mission was already considered a triumph. It had revealed Jupiter in unprecedented detail, discovered volcanoes on Io, hinted at an ocean on Europa, mapped the surfaces of Ganymede and Callisto, and uncovered a ring system. It had also demonstrated the value of the gravitational assist, picking up speed as it slingshotted around the giant planet. Voyager 1's success also set the stage for Voyager 2, which was following a few months behind. While Voyager 1's data was still being analyzed, Voyager 2 was closing in on Jupiter, ready to provide a second complementary perspective. The twin probes together would offer not just snapshots, but a more complete view of the Jovian system, deepening the surprises and raising new questions for decades to come. In July 1979, just months after Voyager 1's close pass, Voyager 2 arrived at Jupiter. Though it followed much the same path, its encounter was no mere repeat. The second probe offered new angles, extended observations, and a chance to confirm or challenge what Voyager 1 had found. Together, the two spacecraft gave humanity a stereoscopic look at Jupiter and its moons, building a more complete picture than either could alone. Voyager 2's approach began with a steady stream of images that improved in resolution as it drew closer. Scientists eagerly compared them with Voyager 1's data, looking for changes and continuity. The Great Red Spot, for example, was again revealed in exquisite detail, its swirling boundaries and embedded vortices standing out clearly. This reinforced the understanding that the storm was not a static feature, but a dynamic weather system, though its longevity remained puzzling. Smaller storms, some forming and dissipating in just days, were also tracked, giving new insight into the chaotic energy of Jupiter's atmosphere. The spacecraft's instruments confirmed the presence of lightning in the cloud tops, as well as the intense radio emissions tied to the planet's magnetic field. Voyager 2's extended observations helped map how these phenomena shifted over time, showing that Jupiter's environment was not only powerful but variable. The magnetosphere, enormous and filled with charged particles, was found to interact with the solar wind in complex ways, creating shock waves and currents that dwarfed anything experienced on Earth. The moons once again stole the spotlight. Voyager 2 passed Io and confirmed what had seemed almost too astonishing from Voyager 1, the presence of active volcanoes. Its cameras captured fresh eruptions and the aftermath of earlier plumes, showing how quickly the surface was being reshaped. Some volcanic deposits had already changed since Voyager 1's pass just months before, underlining the relentless activity. This made Io the most geologically active body in the solar system, driven by the tidal heating of Jupiter's gravity. Europa too came into sharper focus. Voyager 2's images revealed even more of the fractured ice plains, the long ridges, and the strange patterns that suggested motion in the crust. While no one could prove the existence of a subsurface ocean at the time, the evidence mounted that Europa was not a simple frozen world, but one with hidden processes beneath its shell. These observations would later inspire entire missions dedicated to exploring the moon's habitability. Ganymede, the solar system's largest moon, displayed further details of its dual terrain. Voyager 2 showed that the grooved regions were more extensive than first thought, likely the result of tectonic stretching and resurfacing. Its magnetic field, hinted at but not confirmed at the time, would become clearer in later missions. Callisto's battered face, heavily cratered and ancient, again provided a contrast, a relic of the solar system's early history, largely unchanged for billions of years. One of Voyager 2's unique contributions was its imaging of Jupiter's faint ring system at different lighting angles. These views confirmed that the rings were composed mostly of small dust particles, probably ejected from tiny moons by micrometeorite impacts. Unlike Saturn's bright, icy rings, Jupiter's were subtle and tenuous, easily missed without the close-up vantage Voyager provided. The discovery added to the growing realization that ring systems were not unique to Saturn, but a common feature among the giant planets. Another highlight of Voyager 2's encounter was the detailed measurement of Jupiter's radiation environment. Instruments endured intense bombardment, providing crucial data for future mission planning. The radiation belts were found to be stronger and more variable than expected, posing significant challenges for spacecraft electronics and any hypothetical crewed missions in the distant future. While much of the public's attention focused on the breathtaking images, scientists were equally fascinated by the quantitative data pouring in. Plasma detectors, spectrometers, and magnetometers all built a layered understanding of Jupiter as a complex system. It was not just a planet, but a miniature solar system in its own right, with moons, rings, magnetic fields, and radiation belts interacting in ways that made it both beautiful and hazardous. Voyager 2's flyby also reinforced the practical value of having two spacecraft. Instruments on one could back up the other, data gaps could be filled, and unexpected discoveries could be confirmed. The twin missions provided a scientific redundancy that turned out to be invaluable. If only one spacecraft had flown, many of the discoveries might have been doubted or missed entirely. As Voyager 2 left Jupiter behind, it carried with it not only fresh momentum from its gravitational assist, but also a wealth of new knowledge. The twin probes had transformed Jupiter from a distant, fuzzy orb into a world of storms, volcanoes, icy crusts, and tenuous rings. The revelations about Io and Europa alone were enough to rewrite textbooks and ignite new fields of study. And yet, for Voyager 2, the greatest adventures still lay ahead. Its trajectory would carry it on to Saturn and, if luck held, to Uranus and Neptune as well. For now, Jupiter stood as a testament to the mission's success. The twin flybys had delivered more than anyone had expected, revealing a planetary system that was both more dangerous and more fascinating than imagined. Voyager had proven itself not just a working spacecraft, but a true explorer, capable of showing humanity things it had never even dreamed to expect. By late 1980, Voyager 1 was approaching Saturn, the second great target of its mission, and the planet that had fascinated astronomers for centuries with its iconic rings. The excitement surrounding the encounter was immense. While telescopes on Earth and in orbit had long shown Saturn's beauty, they lacked the resolution to reveal the finer details. Voyager 1 promised to peel back that veil and transform Saturn from a distant jewel into a tangible world with moons, weather, and dynamic rings. As the spacecraft neared, its cameras captured Saturn's bands of muted yellow, gold, and gray. Unlike Jupiter's bold stripes, Saturn's atmosphere appeared more subdued, yet Voyager revealed subtle structures within the clouds. These patterns showed that Saturn, too, was an active world with jet streams and storms, though its atmosphere was colder and less turbulent than Jupiter's. Instruments measured wind speeds exceeding 1,000 kilometers per hour, about 620 miles per hour, among the fastest in the solar system. The rings dominated both the imagery and the science. Long known to be composed of icy particles, the rings were revealed by Voyager to be far more complex than anyone expected. Instead of just a few broad bands, the spacecraft showed thousands of narrow ringlets, some just a few kilometers wide. Gaps, waves, and mysterious structures hinted at gravitational interactions with Saturn's moons and perhaps unseen bodies embedded within the rings. The Cassini division, a prominent gap visible from Earth, was shown to contain many faint ringlets rather than being empty. Even more surprising were the spokes, dark radial features that seemed to rotate along with the rings, defying easy explanation. Voyager also discovered that Saturn's rings were not uniform in thickness. Some were surprisingly thin, only tens of meters deep, while others were more substantial. The intricate structure suggested a dynamic system shaped by constant collisions, gravitational nudges, and the shepherding effects of small moons. These findings revealed the rings as a laboratory for studying the physics of disks, with implications not just for Saturn, but for understanding how planets and even galaxies form. The moons of Saturn were no less remarkable. Voyager 1 made close passes by several, revealing them in detail for the first time. Mimas, with its giant Herschel crater, resembled a battered Death Star. Enceladus appeared bright and smooth, suggesting a young surface. Tethys, Dione, and Rhea displayed varied terrains of craters and ridges. Each moon seemed to tell a different story, shaped by collisions, internal processes, and interactions with Saturn's environment. The crown jewel of Voyager 1's Saturn encounter was Titan. This large moon, bigger than Mercury, had long been of special interest because of its thick atmosphere. Telescopic studies had shown that Titan was wrapped in a dense haze, obscuring its surface. Voyager 1's instruments confirmed that the atmosphere was mostly nitrogen, with significant amounts of methane and other hydrocarbons. The pressure at the surface was greater than Earth's, making Titan the only moon in the solar system with a substantial atmosphere. Unfortunately, the haze was so opaque that Voyager's cameras could not see the surface. Still, the confirmation of a dense, nitrogen-rich atmosphere was a landmark discovery. Scientists speculated that Titan might host lakes or oceans of liquid hydrocarbons, and perhaps even prebiotic chemistry resembling conditions on early Earth. This discovery cemented Titan as one of the most intriguing worlds in the solar system and a prime target for future missions. The encounter with Saturn was also the turning point for Voyager 1's trajectory. After its flyby of Titan, the spacecraft's path was bent sharply upward, out of the plane of the planets. This maneuver allowed the close Titan observations, but meant Voyager 1 would not continue on to Uranus and Neptune. Instead, it was set on a course that would carry it out of the solar system forever. This decision reflected the mission's priorities. Titan's mysteries were too compelling to pass up, even at the cost of further planetary flybys. The data from Saturn poured in through late 1980, stunning scientists and the public alike. The complexity of the rings, the diversity of the moons, and the richness of Titan's atmosphere all underscored how little was known before Voyager. Each discovery raised new questions. What caused the ring's spokes? Was Enceladus geologically active? What lay beneath Titan's haze? Voyager 1 had delivered answers, but also mysteries, ensuring that Saturn would remain a focus of planetary science for decades. It had fulfilled its role as a pathfinder, showing that the outer planets were not static and predictable, but dynamic, surprising, and endlessly fascinating. As Voyager 1 headed away from Saturn and toward interstellar space, it left Voyager 2 to carry the torch forward, bound for Saturn in its own right and beyond. In August 1981, less than a year after its twin's dramatic Titan flyby, Voyager 2 reached Saturn. Unlike Voyager 1, whose trajectory carried it out of the planetary plane after Saturn, Voyager 2's path was carefully chosen to allow it to continue onward to Uranus and Neptune. This meant that Voyager 2 would spend less time with Titan, but in exchange, it would give humanity its only opportunity to see the ice giants up close. Even so, its Saturn encounter yielded a wealth of discoveries that built upon and expanded the foundation laid by Voyager 1. As Voyager 2 approached Saturn, the planet's serene appearance was once again shattered by detail. Images revealed the soft pastel bands of the atmosphere, and closer inspection showed jet streams and storms similar to those seen by Voyager 1. Saturn's winds were clocked at extraordinary speeds, sometimes surpassing 1,500 kilometers per hour, 930 miles per hour. These winds, driven by heat from the planet's interior and modulated by its rotation, painted the upper atmosphere with subtle, ever-shifting structures. The ring system, already revealed as complex by Voyager 1, became even more fascinating in Voyager 2's images. Thousands of narrow ringlets appeared with unprecedented clarity, along with new gaps and wave-like features. The spacecraft confirmed that the so-called spokes were real, not artifacts, and that they appeared and disappeared over time. These mysterious radial streaks of material seemed to defy the neat orbital motions of the ring particles, possibly caused by electrostatic forces or magnetic interactions. Voyager 2 also provided sharper measurements of the ring composition. Spectrometers confirmed that the rings were mostly water ice, mixed with dust and other contaminants. The brightness of the rings varied depending on viewing angle, suggesting that particle sizes and densities differed across the system. Some regions were dominated by larger chunks, others by fine dust. The rings were not static, but dynamic, shaped by collisions, clumping, and gravitational nudges from Saturn's moons. Speaking of moons, Voyager 2 gave humanity new views of several Saturnian satellites. Enceladus, in particular, surprised scientists with its bright, reflective surface. Unlike many heavily cratered moons, Enceladus appeared remarkably smooth in some areas, with fresh-looking terrains that hinted at geological activity. Though Voyager 2 could not prove it, later missions would confirm that Enceladus harbors subsurface oceans and active geysers that spray water vapor into space. At the time, however, even the suggestion that such a small moon could be geologically alive was remarkable. Voyager 2 also revealed new details of Tethys, Dione, and Rhea, moons that bore scars of tectonic fractures and craters from ancient impacts. Each had its own distinct character, evidence of a varied history within the Saturnian system. Mimas, already famous for its giant Herschel crater, was imaged in greater detail, solidifying its reputation as one of the most heavily scarred bodies in the solar system. Titan once again commanded attention, though Voyager 2's flyby was more distant than Voyager 1's. The dense, hazy atmosphere was confirmed to be nitrogen-rich, with methane and hydrocarbon compounds. Voyager 2's measurements strengthened the case that Titan's chemistry resembled that of early Earth, though no surface details could be seen. The tantalizing hints of lakes or seas remained unresolved mysteries left for future missions like Cassini and Huygens to explore. Voyager 2's instruments also provided more precise measurements of Saturn's magnetosphere. The data confirmed that it was vast and complex, extending far into space and interacting with the solar wind in ways similar to, but less extreme than Jupiter's. The magnetosphere also played a role in shaping the rings and affecting the surfaces of Saturn's moons, particularly those orbiting within its radiation belts. Another highlight of Voyager 2's Saturn encounter was the gravitational assist it received. Just as Jupiter had flung the spacecraft toward Saturn, Saturn now bent Voyager 2's path toward Uranus. The trajectory was carefully planned, a close enough pass to gather valuable science, but precise enough to ensure the right alignment for the next leg of the journey. This maneuver underscored the brilliance of the Grand Tour design, a ballet of celestial mechanics that allowed a single spacecraft to visit 4 giant planets. The success of Voyager 2 at Saturn reaffirmed the mission's importance. With 2 sets of encounters, scientists had data to compare and contrast, revealing both the consistency and variability of Saturn's system. Where Voyager 1 had raised questions, Voyager 2 often added new clues or entirely new mysteries. Together, the twin spacecraft transformed Saturn from a beautiful but largely enigmatic planet into a dynamic world with active moons, shifting rings, and a rich atmosphere. For the public, the images were unforgettable. Saturn's rings, with their delicate structures, looked almost like works of art. The moons, each distinct and strange, expanded humanity's understanding of the diversity of planetary systems. Titan remained veiled, but the promise of its secrets lingered, sparking decades of fascination. With Saturn behind it, Voyager 2 turned its instruments toward the next great unknown, Uranus. It would take nearly 5 years to reach the pale blue planet, giving engineers and scientists time to rest, recalibrate, and prepare. But by the time Voyager 2 left Saturn in 1981, it had already cemented its place in history. It had delivered a treasure trove of discoveries, extended the mission's reach, and set the stage for humanity's only encounters with the ice giants that lay ahead. After the drama of the Saturn encounters, Voyager 2 entered what mission planners called a cruise phase. It had left Saturn behind in August 1981 and was now on a 5-year journey to Uranus, a planet that no spacecraft had ever visited. This long interlude between planetary flybys was anything but wasted time. For scientists and engineers, it was an opportunity to refine techniques, plan new strategies, and squeeze every possible bit of science out of the spacecraft as it coasted through the vastness of the outer solar system. Voyager 2's trajectory was now locked on a narrow corridor that would take it to Uranus in January 1986. The precision of this path was remarkable. Any significant error during the Saturn encounter could have doomed the mission, missing Uranus entirely or passing too far away to collect meaningful data. But the gravitational assist had worked exactly as intended. Voyager 2 was on track, moving at more than 15 kilometers per second, about 34,000 miles per hour, relentlessly closing the distance. During this cruise, Voyager continued to measure the interplanetary environment. Instruments recorded the solar wind and the influence of the sun's magnetic field far from Earth. Cosmic ray detectors measured high-energy particles arriving from distant parts of the galaxy. This information was valuable because it helped map the heliosphere, the bubble of solar influence that surrounds the planets, and showed how it changed with distance. While the planets offered moments of dramatic revelation, the slow accumulation of data in between filled gaps in humanity's understanding of space itself. One of the main challenges during the cruise was power management. By the early 1980s, the output of Voyager's plutonium-fueled generators was declining. Engineers at NASA's Jet Propulsion Laboratory had to carefully ration which instruments stayed on continuously and which could be cycled on only when needed. This balancing act would become more critical as the years wore on, but even then, it was clear that efficiency was the key to prolonging the spacecraft's life. Communication also became more difficult with distance. By the mid-1980s, Voyager 2 was more than 2.5 billion kilometers, about 1.6 billion miles, from Earth. At that range, a radio signal took more than 2 hours to travel one way. Data rates slowed to a crawl compared to earlier phases of the mission, and every transmission had to be carefully scheduled through the deep. Space Network's massive antennas. Upgrades on Earth, including more sensitive receivers and arrayed dishes, helped ensure that even the faintest signals from Voyager could still be detected. The cruise period was also crucial for planning the Uranus flyby. Unlike Jupiter and Saturn, Uranus was relatively unknown. Telescopes had shown it to be a pale blue-green disk with a faint ring system and a few visible moons. But its extreme tilt, rotating on its side with its poles near where its equator should be, posed unique challenges. Voyager's encounter geometry would be unlike any before, requiring scientists to rethink how to program the spacecraft's instruments. Every observation, every camera sequence had to be rehearsed in advance. Meanwhile, engineers had to keep the spacecraft healthy through the long cruise. Occasional glitches cropped up. False alarms, small malfunctions, or unexpected behavior in the instruments. But the mission team became adept at diagnosing problems and uploading fixes. The spacecraft's computers, limited as they were by modern standards, proved remarkably adaptable. Commands could be rewritten and reloaded, effectively giving Voyager a kind of flexibility that extended its usefulness well beyond what had been imagined in the 1970s. This long period also allowed the public's anticipation to build. By the mid-1980s, space exploration had gone through cycles of excitement and disappointment, and the prospect of a new, first-ever planetary encounter stirred interest once again. For many, Uranus was a mystery, rarely studied in detail and often overlooked. Voyager 2 promised to change that, turning a pale dot into a world with character, history, and surprises of its own. By the end of 1985, Voyager 2 was closing in. The first images of Uranus began to trickle back, tiny disks, slowly sharpening as the spacecraft approached. The team braced for another whirlwind of discovery. Just as at Jupiter and Saturn, years of careful planning and quiet cruise would culminate in a brief, intense window of exploration. After half a decade of silent travel, Voyager was about to open humanity's eyes to another new planet. When Voyager 2 reached Uranus in January 1986, it was a moment unlike any other in the history of planetary exploration. No spacecraft had ever been this far, and no close-up images of Uranus or its moons had ever been seen. What had once been little more than a bluish smudge in telescopes suddenly became an alien world, revealed in detail for the very first time. Voyager 2's trajectory carried it within about 81,500 kilometers, 50,600 miles, of the planet's cloud tops. As the spacecraft approached, it began sending back sharper and sharper images of the pale blue orb. Scientists were immediately struck by its featureless appearance. Unlike Jupiter with its swirling storms or Saturn with its bold bands and rings, Uranus looked calm, almost eerily so. The bland disk frustrated some meteorologists who had hoped for dramatic atmospheric activity, but it also intrigued them. What could make a planet so quiet? Later analysis suggested that Uranus's extreme tilt and cold temperatures might suppress the kind of weather seen elsewhere, though faint cloud features were eventually teased out from the data. The rings of Uranus, discovered in 1977, were also imaged in detail for the first time. Voyager 2 revealed that they were dark, narrow, and made up of relatively large particles compared to the dustier rings of Saturn. The spacecraft found 11 rings, with peculiar clumps and braids hinting at complex gravitational interactions. Scientists suspected that small moons, acting as shepherds, kept the rings confined in their sharp edges. This suspicion was confirmed when Voyager 2 discovered two such moons, Cordelia and Ophelia, orbiting close to the outer ring. Perhaps the greatest surprise of the Uranus encounter was the planet's magnetic field. Instead of being centered and aligned roughly with the planet's axis, like Earth's, Uranus's magnetic field was tilted almost 60 degrees and offset far from the planet's core. This meant that as the planet rotated on its side, its magnetosphere wobbled and twisted in bizarre ways. The field lines swept through space in corkscrew-like patterns, baffling scientists and hinting at unusual processes deep within the planet. Voyager 2 also transformed Uranus from a world with 5 known moons into a world with 27. During the flyby, the spacecraft discovered 10 new small moons, most of them irregular, dark bodies only a few tens of kilometers across. The larger moons were studied in detail, and here again surprises abounded. Miranda, the innermost of the Big Five, revealed a tortured surface unlike anything seen before. Huge cliffs, patchwork regions, and giant fault canyons suggested a history of violent geological upheaval. Some scientists speculated that Miranda may have been shattered and reassembled in the past, giving it a Frankenstein-like appearance. Ariel showed signs of recent resurfacing, with bright areas that may have been caused by icy volcanism or other cryogenic processes. Titania and Oberon, the largest moons, displayed old cratered terrains mixed with fault lines that suggested tectonic activity. Umbriel, by contrast, appeared darker and more heavily cratered, its surface older and less geologically active. Each moon was a world in miniature, with its own story to tell. The Uranus encounter also carried emotional weight beyond science. In January 1986, just days after Voyager 2's closest approach, the Space Shuttle Challenger disaster shocked the world. The triumph of exploring Uranus was overshadowed by tragedy, a reminder of the risks of space exploration, both robotic and human. Yet the data from Voyager 2, arriving in the same days as the morning, also underscored the resilience of exploration and the idea that humanity's reach was still expanding, even in difficult times. The flyby lasted only a matter of hours in its closest phases, but the science it produced would occupy researchers for decades. By the time Voyager 2 sped away, bound for Neptune, it had rewritten the book on Uranus. It revealed a planet of extremes, tipped on its side, wrapped in a lopsided magnetic field, circled by strange rings, and orbited by a family of moons that defied expectations. For a planet that had once seemed dull, Uranus turned out to be a place of deep and peculiar mysteries. As Voyager 2's cameras shut down their final sequences, the spacecraft was already on its way to yet another first. It was heading toward Neptune, the last planet it would ever visit. Humanity had touched Uranus for the first time, and though the spacecraft would never return, the knowledge it left behind guaranteed that Uranus would never again be ignored or underestimated. After the Uranus encounter in January 1986, Voyager 2 continued its relentless journey outward. The spacecraft had just delivered humanity's only close-up look at Uranus, but there was no time to pause. Its trajectory had been carefully plotted to send it on a gravitational slingshot toward Neptune, the last unexplored giant. This leg of the mission was long, spanning more than 3 years, and it became a period of quiet endurance for both spacecraft and scientists. Voyager 2 traveled more than 1 billion kilometers between Uranus and Neptune. As it drifted through this vast stretch of darkness, it continued to function with remarkable reliability. The spacecraft was already well beyond its intended lifespan, operating on dwindling power reserves and equipment that had been launched nearly a decade earlier. Each command sent from Earth took more than 4 hours to arrive, a reminder of how far Voyager 2 had ventured from home. Though the Neptune encounter was still years away, scientists used the cruise period to refine their plans. The lessons learned at Jupiter, Saturn, and Uranus had shown that each planet could surprise them, and Neptune was still largely a mystery. Telescopic observations from Earth provided only the faintest details. In preparation, the mission team designed carefully orchestrated sequences for imaging, magnetometer scans, plasma studies, and atmospheric observations. Every action had to be planned months in advance, since real-time control was impossible. Voyager 2 also continued to collect valuable interplanetary science during this period. Its instruments studied the solar wind, cosmic rays, and magnetic fields in the outer reaches of the solar system. These observations were essential for building a complete picture of how the sun's influence extended far into space. Even in the absence of a nearby planet, the spacecraft was doing frontier science. The cruise from Uranus to Neptune was not without tension. With each passing year, the spacecraft's power supply, its plutonium-powered radioisotope thermoelectric generators, declined in output. Engineers had to carefully ration which instruments could be used at any given time, shutting down heaters and systems that were not critical. The goal was to keep Voyager 2 alive long enough to reach Neptune. It was a delicate balance between conservation and readiness. On Earth, the Challenger disaster of 1986 cast a long shadow over NASA's human spaceflight program, but Voyager became a symbol of continuity and success. As the space shuttle fleet was grounded and confidence shaken, Voyager pressed on silently, carrying the torch of exploration into realms no human had ever seen. Anticipation grew as Neptune approached. The encounter would be the grand finale of the Voyager planetary mission, the last chance to see a new planet up close for perhaps decades to. Scientists debated priorities. Should the focus be Neptune's turbulent atmosphere, its faint rings, or its intriguing moon Triton? Every hour of observation time would count, and the team wanted to make the most of this once-in-a-lifetime opportunity. Meanwhile, the spacecraft itself provided reassurance. Despite being more than 12 years into its journey, Voyager 2 remained responsive, its instruments still performing, its systems still communicating. Each weekly status update confirmed that the spacecraft was holding steady, its resilience a testament to the engineers who had designed it in the 1970s with durability in mind. By the late 1980s, as Neptune grew nearer, ground-based observations began to hint at surprises. The planet appeared to have dynamic weather, with shifting cloud patterns and possible storms. Its moon Triton, seen only as a point of light from Earth, was speculated to be unusual, perhaps geologically active. These teasers only heightened the sense of suspense as Voyager 2 closed in. By 1989, all eyes were on Neptune. Voyager 2 was approaching the end of its grand tour, but also the climax. The years between Uranus and Neptune had been years of patience, planning, and careful conservation, but they had also built a sense of drama. For the first time in history, humanity was about to see the last of the solar system's major planets up close. The spacecraft that had begun its journey as one of 2 probes in 1977 was now carrying the hopes of an entire generation of scientists eager for one final revelation. As Voyager 2 closed the gap toward Neptune, the mission entered its final planetary act. By 1988, the spacecraft had traveled so far that Neptune was just a pale dot in its cameras, but every passing week brought it closer. Engineers and scientists at NASA knew they had one shot to capture this distant world in detail. Unlike Jupiter or Saturn, which had been visited by multiple missions, Neptune's exploration depended entirely on Voyager 2. If something went wrong, humanity would be left with little more than blurred telescope images for decades to come. The spacecraft began its official approach sequence in mid-1989, with carefully programmed commands loaded into its computer. Because of the long communication delay, over 4 hours for a signal to travel each way, every maneuver had to be pre-planned, with almost no opportunity for mid-course corrections. This was choreography on a cosmic scale, requiring absolute precision. In the months before closest approach, Voyager 2 started taking images of Neptune that surpassed anything seen from Earth. The planet revealed itself as a striking deep blue orb, its color caused by methane absorbing red light and scattering blue. Unlike Uranus, which appeared relatively bland and uniform, Neptune's atmosphere looked active and dynamic. Even from afar, the spacecraft's cameras caught hints of storms and cloud features, suggesting a turbulent and energetic world. The anticipation built with each new image. Scientists eagerly awaited data from the spacecraft's suite of instruments. They wanted to know Neptune's exact mass, its magnetic field, the speed and direction of its winds, and the nature of its thin ring system, which had only been hinted at by ground-based stellar occultation studies. Most of all, they were curious about its large moon Triton, which might hold surprises of its own. As Voyager 2 approached, the mission team faced the immense challenge of allocating limited resources. The spacecraft did not have the power to run every instrument continuously, and memory space for storing data was limited. Hard choices had to be made about what to prioritize: atmospheric studies, magnetospheric measurements, or imaging of moons and rings. Each second of observation time was weighed against another potential target. The approach to Neptune also provided an opportunity for navigation teams to flex their skills. By measuring the apparent position of the planet and its moons in Voyager's images, they could fine-tune the spacecraft's trajectory with small thruster burns. These adjustments were critical for ensuring Voyager passed through the precise corridor that would give the best scientific return and still slingshot the spacecraft onto its post-Neptune trajectory out of the solar system. In the weeks leading up to closest approach, Voyager 2's pictures of Neptune became front-page news. For the public, the images were a reminder of the grandeur of space exploration and the extraordinary distances involved. This was the first time anyone had seen Neptune in detail, and the rich blue world quickly captured imaginations. For scientists, each picture was data, each cloud feature a puzzle waiting to be solved. As the spacecraft drew nearer, the mission team grew increasingly focused. Years of planning and months of preparation now hinged on a critical window of just a few days in August 1989. The spacecraft would sweep past Neptune at more than 90,000 kilometers per hour, about 56,000 miles per hour, collecting data in a rapid-fire sequence that could never be repeated. Every camera frame, every magnetometer reading, every signal from its instruments had to be executed flawlessly. Voyager 2's approach was also a race against time. The spacecraft was already more than a decade old, and its power supply was dwindling. This was its last chance to provide close-up views of a new planet. If it succeeded, it would complete the grand tour that had begun with Jupiter 12 years earlier, closing the chapter on humanity's first exploration of the outer solar system. By late August, Neptune filled Voyager 2's camera frames. Its atmosphere swirled with storms, including a massive dark oval that scientists dubbed the Great Dark Spot. High-altitude white clouds raced across its skies, some casting shadows onto the layers below. It was a world of motion and mystery, more dynamic than Uranus, and unlike any other planet seen before. The approach was already rewriting textbooks, and the best was yet to come. When Voyager 2 finally reached Neptune in August 1989, one of its most startling discoveries was the presence of a massive storm system dominating the southern hemisphere. This storm was quickly named the Great Dark Spot, echoing the Great Red Spot of Jupiter, though the two phenomena turned out to be quite different in both character and lifespan. The discovery of the Great Dark Spot transformed Neptune from a distant, mysterious ice giant into a dynamic, restless planet with weather as violent as any in the solar system. The Great Dark Spot measured about 13,000 kilometers, roughly 8,000 miles, across, about the size of Earth itself. In Voyager's images, it appeared as a dark oval swirling within Neptune's bright blue atmosphere. Like Jupiter's famous storm, it was an anticyclone, meaning a high-pressure system where winds spun around the center. But unlike Jupiter's storm, which has lasted for centuries, Neptune's Great Dark Spot was a transient feature, vanishing only a few years after Voyager's flyby. This raised new questions about the nature of weather in Neptune's extreme environment. Voyager's instruments revealed that winds around the Great Dark Spot reached speeds of up to 2,100 kilometers per hour, about 1,300 miles per hour, the fastest ever recorded in the solar system. These supersonic winds blew in the opposite direction to Neptune's overall rotation, creating a swirling, chaotic system of atmospheric bands and eddies. The scale of energy required to sustain such winds in a frigid, distant world was astonishing, and scientists quickly began rethinking what they thought they knew about planetary atmospheres. Another striking feature observed by Voyager was a series of bright, high-altitude clouds nicknamed scooters. These small, fast-moving clouds zipped around Neptune just above the Great Dark Spot, crossing the planet in as little as 16 hours. They seemed to be made of frozen methane crystals and were carried along by the violent winds. Their speed and persistence made them useful for tracking atmospheric dynamics, as they provided visible markers of the otherwise invisible motion of gases in Neptune's upper atmosphere. The Great Dark Spot wasn't the only storm system Voyager observed. A smaller dark oval, referred to as the Dark Spot 2, appeared in the northern hemisphere. It, too, was accompanied by bright methane clouds, suggesting that Neptune was a planet with multiple storm systems coexisting in its atmosphere. Voyager also imaged a bright feature called the scooter cloud, separate from the storms but equally puzzling in its behavior. The discovery of multiple storm systems hinted that Neptune's atmosphere was in constant flux, more comparable to Earth's dynamic weather than to the more stable giants like Jupiter. What puzzled scientists most was how Neptune could sustain such powerful winds and storms despite being so far from the sun. At Neptune's distance, sunlight is only about 1/1000th as strong as it is at Earth, providing little energy to drive atmospheric motion. The answer seemed to lie within Neptune itself. Voyager's data suggested that Neptune radiates more than twice as much heat as it receives from the sun, likely due to residual heat left over from its formation, and perhaps from internal processes, such as the slow compression of its atmosphere. This internal heat provided the energy to power Neptune's supersonic winds and constantly shifting weather. The fleeting nature of Neptune's storms also set them apart from the long-lived systems of Jupiter and Saturn. When the Hubble Space Telescope observed Neptune in the 1990s, the Great Dark Spot had already disappeared, replaced by new storm systems in different locations. This meant that Neptune's atmosphere is extraordinarily dynamic, with giant storms forming and dissipating over just a few years. Unlike Jupiter's weather, which can remain stable for centuries, Neptune's storms behave more like extreme versions of Earth's hurricanes, rising and fading in relatively short timescales. Voyager's images of Neptune's stormy atmosphere provided a wealth of data, but also raised enduring mysteries. Why do Neptune's winds blow so fast? What controls the formation and disappearance of its dark spots? How do methane clouds and deep atmospheric layers interact to create the visible weather patterns? Decades later, many of these questions remain unanswered. As no spacecraft has returned to Neptune since Voyager 2, the Great Dark Spot and its companions were more than just striking features in Voyager's photographs. They were a revelation about the nature of the outer planets. Neptune, once assumed to be cold and static, turned out to be one of the most dynamic planets in the solar system. Its atmosphere alive with storms, clouds, and winds that defy easy explanation. The discoveries gave scientists a new perspective on ice giants, highlighting their complexity and ensuring that Neptune would remain a target of fascination for future exploration. Of all the discoveries Voyager 2 made at Neptune, perhaps the most astonishing came not from the planet itself, but from its largest moon, Triton. Before Voyager's arrival, Triton was little more than a faint dot of light in telescopes, with astronomers knowing only that it was unusually large for a moon and followed a strange retrograde orbit, circling Neptune in the opposite direction of the planet's rotation. Many suspected this meant Triton was not a native moon, but a captured object, perhaps from the Kuiper Belt. Voyager's flyby confirmed those suspicions and revealed a world as bizarre as it was beautiful. Voyager 2's cameras captured Triton as a pale, pinkish world with a smooth, icy surface. At 2,710 kilometers, about 1,680 miles across, Triton is nearly as large as Earth's moon and is the seventh largest moon in the solar system. Its retrograde orbit immediately set it apart, as no other large moon in the solar system shares this trait. Such an orbit strongly suggests that Triton was once an independent object, possibly a dwarf planet similar to Pluto, that Neptune captured long ago through a gravitational encounter. The surface of Triton turned out to be one of the most unusual Voyager had ever seen. Instead of being heavily cratered like most moons, Triton's surface was remarkably smooth in many areas, indicating recent geological activity. Vast plains of frozen nitrogen and methane stretched across the landscape, broken by ridges, troughs, and strange patterns that looked almost like the skin of a cantaloupe. This cantaloupe terrain remains unique in the solar system, and its origin is still debated. Some scientists think it formed from convection beneath the icy crust, while others suspect past cryovolcanism, volcanoes that erupt not molten rock, but slurries of water, ammonia, and methane. Even more dramatic were Voyager's observations of active geysers on Triton. In one of the great surprises of planetary exploration, the spacecraft detected plumes of nitrogen gas erupting from the surface, shooting up as high as 8 kilometers, about 5 miles, before being carried downwind to form long, dark streaks across the ice. These geysers were the first active eruptions seen on any icy body, proving that Triton was geologically alive. The activity seemed to be driven by seasonal warming. Thin layers of frozen nitrogen on the surface absorbed sunlight, built up pressure beneath them, and then erupted explosively. Triton also possesses a thin but significant atmosphere, primarily nitrogen with traces of methane. Voyager's instruments measured its pressure at less than 0.01 times that of Earth's atmosphere, making it extremely tenuous but still enough to sustain winds that help spread the geyser plumes. This atmosphere is likely in equilibrium with surface ices, freezing and sublimating as Triton's seasons change during its 165-year orbit around the Sun. The discovery of such an atmosphere on a moon so far from the Sun was unexpected and underscored how diverse planetary bodies can be. The temperature at Triton's surface is among the coldest measured in the solar system, around 38 Kelvin, minus 235 degrees Celsius, or minus 391 degrees Fahrenheit. Yet paradoxically, this frozen world showed some of the most dynamic activity ever observed on a moon. Its combination of nitrogen ice, volatile gases, and internal heat sources created a landscape in constant flux, where geysers erupted, surfaces renewed themselves, and unique terrains formed. Triton's orbit provides further clues to its history. Its retrograde motion and tilted inclination suggest that its capture disrupted Neptune's original system of moons, perhaps scattering or destroying many of them. The capture may have also generated immense tidal heating within Triton, helping to explain its unusual geology and relatively young surface. In some ways, Triton may be a preview of what awaits in the Kuiper Belt, where Pluto and other icy bodies reside. Voyager's images of Triton in 1989 offered the first detailed look at a world that resembled those distant objects, making it a bridge between the solar system's planets and its small, icy frontier. For planetary scientists, Triton quickly became a world of fascination. It combined traits of icy moons like Europa with features of dwarf planets like Pluto, yet was unlike either. Its geysers showed that geologic activity was not limited to Earth, Mars, or Io, but extended to icy bodies in the outer solar system. Its surface suggested processes no one had imagined before. Its orbit hinted at a violent past involving capture and disruption. Every detail Voyager revealed about Triton raised new questions, making it one of the most intriguing targets for future exploration. The flyby of Triton was fleeting, lasting only a matter of hours, but its impact was lasting. Scientists often cite it as one of the highlights of Voyager's entire mission, a discovery that expanded humanity's sense of what kinds of worlds might exist beyond Earth. Triton showed that even in the frigid reaches of the solar system, worlds could be active, evolving, and surprising. More than 30 years later, Voyager's pictures of Triton remain the best we have, and the moon continues to stand as a compelling target for new missions. While Voyager 2's close encounter with Neptune revealed the planet's turbulent atmosphere and the strange world of Triton, it also uncovered another fascinating system, Neptune's faint, dusty rings and its collection of small moons. Before the flyby, scientists weren't even sure if Neptune had a proper ring system. Ground-based observations in the 1980s had hinted at partial arcs of material, but telescopes could not resolve them clearly. Voyager 2 settled the question once and for all, showing that Neptune does indeed have rings, though they are far less prominent than the majestic ones surrounding Saturn. The spacecraft identified at least 5 distinct rings, each made up of small particles of dust and ice. These rings were named after prominent figures connected with the study of Neptune: Gale, Leverrier, Lassell, Arago, and Adams. Unlike Saturn's broad and bright rings, Neptune's are thin, dark, and incomplete looking in places. Some appeared clumpy with denser arcs of material separated by more diffuse regions. This uneven distribution puzzled scientists, as gravitational forces should normally smooth out such variations over time. The key to this mystery seemed to lie in Neptune's moons. Several small inner satellites orbit close to the rings, and their gravitational influences may act as shepherds, corralling particles into arcs and clumps instead of evenly spreading them out. This shepherding effect is similar in principle to what Saturn's moons do for its rings, though Neptune's system operates on a subtler and less visually striking scale. The Adams ring, in particular, contained distinct arcs, concentrations of material that defied easy explanation. How these arcs persist over time remains an open question, and it is thought that nearby moons play a stabilizing role. In addition to the rings, Voyager 2 discovered 6 new small moons orbiting Neptune, adding to the 2 already known from Earth-based observations. These moons, with irregular shapes and heavily cratered surfaces, are thought to be captured or fragmented bodies, remnants of the processes that shape Neptune's outer system. Some of the closest moons, like Naiad, Thalassa, Despina, and Galatea, orbit just beyond the planet's cloud tops and interact dynamically with the rings. Galatea, in particular, seems to play a role in maintaining the arcs in the Adams ring, acting as a gravitational shepherd. Further out, Voyager also imaged the moons Larissa and Proteus. Proteus stood out as the largest of Neptune's inner moons, measuring about 400 kilometers, roughly 250 miles, across. Despite its size, it is irregularly shaped, more like a lumpy rock than a sphere. This suggests that Proteus never had enough internal heat to reshape itself into a round body under gravity. Its heavily cratered surface shows it has been battered by impacts for billions of years. Voyager's pictures of Proteus reveal details never before seen of such a large, irregular moon, giving scientists insight into the transitional zone between small, asteroid-like bodies and spherical worlds. Together, Neptune's rings and small moons painted a picture of a complex and active system. The rings may be relatively young, formed from the breakup of a moon or the accumulation of debris captured by Neptune's gravity. Their faint, dusty nature indicates that they are not as stable as Saturn's and may be replenished over time by collisions among the small moons. The moons themselves, locked in delicate gravitational interactions, reveal the chaotic and dynamic processes that shape planetary systems. Although Voyager's brief flyby provided the first close-up look at these features, it also left many questions unanswered. How exactly do the arcs in Neptune's rings remain stable? What are the long-term fates of the inner moons, some of which may eventually spiral inward and break apart? How do these faint rings compare to those of Uranus, which are also dark and thin? Voyager opened the door to these mysteries, but much remains to be explored. The discovery of Neptune's rings and small moons underscored one of Voyager's greatest contributions, the realization that every planet in the outer solar system has rings, even if they are not as spectacular as Saturn's. This was not known before the twin probes were launched, and it reshaped the way scientists think about planetary systems. Rings once thought to be rare turned out to be a common feature, each with its own unique properties. Neptune's understated rings may lack grandeur, but they remain an essential piece of the puzzle in understanding how planets and their satellites evolve. One of Voyager 2's most important contributions to our knowledge of Neptune came not from its cameras, but from its instruments that measured magnetic and plasma environments. Before the encounter, scientists had little idea what Neptune's magnetic field might look like. Would it be similar to Earth's, tilted only slightly from the planet's rotation axis? Would it resemble Jupiter's vast, powerful magnetosphere? Or would it be weak and irregular, given Neptune's smaller size and colder composition? The answers turned out to be surprising and, in many ways, baffling. Voyager 2 discovered that Neptune's magnetic field is both strong and oddly configured. The field is tilted by about 47 degrees relative to the planet's rotational axis, far more than Earth's modest 11-degree tilt. In addition, the magnetic field is not centered within the planet, but offset by several thousand kilometers from the planetary core. This means Neptune's magnetic poles are not neatly aligned with its geographic poles and are instead displaced, creating a lopsided and asymmetric magnetosphere. This unusual geometry was strikingly similar to what Voyager had observed at Uranus just 3 years earlier. Uranus's field is tilted by nearly 60 degrees and also offset from its center. The fact that two neighboring ice giants share this strange characteristic suggested that something about their internal structures produces magnetic fields in a way unlike Earth or the gas giants. Scientists theorize that instead of being generated deep in a molten metal core like Earth's, the magnetic fields of Uranus and Neptune arise from convective motions in a shell of electrically conductive water, ammonia, and methane ices located closer to the surface. If true, this would explain both the tilt and the offset. Voyager's measurements showed that Neptune's magnetic field is comparable in strength to Earth's, despite the planet's much larger size. This meant that the magnetosphere, Neptune's bubble of magnetic influence, extended millions of kilometers into space, shaping how solar wind particles flowed around the planet. The tilted and offset nature of the field caused the magnetosphere to wobble dramatically as Neptune rotated, creating a highly dynamic environment unlike the more stable magnetospheres of Earth, Jupiter, or Saturn. Inside this magnetosphere, Voyager 2 detected complex interactions between charged particles, magnetic fields, and Neptune's moons. Radiation belts of high-energy particles were found to exist. Though they were less intense than those at Jupiter, these belts may have been shaped by interactions with Triton and other moons, which sweep through Neptune's magnetic environment. Another key discovery was the auroras. Curtains of light created when charged particles from the solar wind slam into the atmosphere near magnetic poles. Unlike the stable, oval-shaped auroras of Earth, Neptune's auroras appeared patchy and irregular, a direct consequence of the tilted and off-center field. These findings challenged long-standing models of planetary magnetism and forced scientists to consider a wider range of possibilities for how magnetic fields can be generated. The importance of Neptune's magnetic field extends beyond the planet itself. By studying it, scientists gained a new perspective on planetary dynamos, the processes by which moving conductive materials generate magnetic fields. The unusual cases of Uranus and Neptune provided critical data points that broadened our understanding beyond the relatively straightforward fields of Earth and Jupiter. They showed that magnetic fields could be tilted, off-center, and still powerful, suggesting that exoplanets across the galaxy might display even greater diversity in their magnetospheres. Voyager's findings also had implications for habitability studies. Magnetic fields help shield planets from harmful solar and cosmic radiation, making them important for the potential habitability of worlds. By revealing such unusual magnetic geometries, Neptune and Uranus suggested that protective fields might exist in configurations far different from Earth's, complicating but also enriching the search for life elsewhere. In the end, Neptune's magnetic field became one of Voyager's most intriguing discoveries. It was not the neatly aligned, predictable field many scientists had expected, but something strange, offset, and dynamic. More than 3 decades later, the details of how exactly it is generated remain uncertain, awaiting future missions to provide new data. Voyager's brief flyby left us with as many questions as answers, but it also expanded our imagination about what planetary magnetism can be. The flyby of Neptune in August 1989 marked not only Voyager 2's last close encounter with a planet, but also the final planetary stop of the entire Voyager mission. After more than 12 years of travel and 3 prior planetary encounters, the spacecraft was about to complete its grand tour of the outer solar system. This was the end of one chapter and the beginning of another, where the spacecraft would transition from planetary exploration to a mission focused on interstellar space. The final planetary flyby was an extraordinary success. Voyager 2 passed just 4,950 kilometers, about 3,080 miles, above Neptune's North Pole, making it the closest approach of the entire mission to any planet. The spacecraft then swung outward, passing within 40,000 kilometers, about 25,000 miles, of Triton. These 2 flybys were carefully timed so that a single trajectory could maximize the scientific return from both Neptune and its largest moon. The precision required for this maneuver was astounding, given the spacecraft's immense speed of nearly 90,000 kilometers per hour, about 56,000 miles per hour, and the distance of more than 4.5 billion kilometers, 2.8 billion miles, from Earth. The sequence of observations was carefully choreographed, the product of years of planning and months of final adjustments. Every camera shot, every magnetic field measurement, and every spectrometer reading had to be pre-programmed into Voyager's onboard computers. By the time the data began streaming back to Earth, Voyager was already moving on, and the mission team could only watch and hope that their programming had been perfect. The images and data did not disappoint. In a matter of days, Voyager 2 transformed Neptune from a fuzzy dot into a vivid, living world. The pictures of the Great Dark Spot, the high-speed winds, the bright methane clouds, and the chaotic weather patterns reshaped scientists' understanding of planetary atmospheres. At the same time, the close pass by Triton revealed an alien landscape of nitrogen ice, cantaloupe-like terrain, and geysers erupting into a thin atmosphere, discoveries that no one had predicted. The spacecraft also confirmed Neptune's faint rings and discovered several small moons that had never been seen from Earth. The magnetometer data revealed a magnetic field tilted and offset in bizarre ways, similar to Uranus, further complicating the picture of planetary dynamos. The plasma and particle instruments gave scientists their first close look at how the solar wind interacts with an ice giant's magnetosphere, adding to the broader puzzle of planetary space environments. Perhaps most remarkable was the timing of the encounter. The Voyager team had calculated that by flying past Neptune in just the right way, the spacecraft could use Triton's gravity to bend its trajectory toward the outer solar system. This maneuver gave Voyager 2 the boost it needed to escape the pull of the sun entirely and continue on its journey toward interstellar space. It was an elegant conclusion to the planetary phase of the mission. One final gravity assist, one final close-up view of a new world, and then onward into the unknown. For the mission team, the flyby was bittersweet. After Neptune, there would be no more planetary encounters. The spacecraft had seen all the outer giants, Jupiter, Saturn, Uranus, and Neptune, and there were no more worlds along its path. Many of the scientists and engineers who had spent years preparing for the grand tour knew that this was their last chance to directly study a planet with Voyager. As the spacecraft sped away from Neptune, the golden era of planetary exploration that Voyager represented was coming to an end. Yet, in another sense, the Neptune encounter marked a beginning. With the planetary flybys complete, Voyager's mission was redefined. From that point forward, the focus would be on the By's heliosphere, the vast bubble of space carved out by the sun's magnetic field and solar wind. Voyager 2, like its twin Voyager 1, would become an explorer of deep space, carrying its instruments into regions no spacecraft had ever ventured. The Neptune flyby was a fitting finale, bold, successful, and filled with discoveries that would echo for decades. It brought the grand tour to a triumphant close and reminded humanity of the extraordinary value of persistence, planning, and daring in exploration. Long after August 1989, the images and data from that brief encounter continued to inspire new generations of scientists and dreamers. With Neptune and Triton now behind it, Voyager 2 crossed a symbolic threshold. The planetary phase of its mission, the part that had defined its public identity and brought stunning discoveries, was complete. From this point forward, the spacecraft's role shifted. It was no longer a planetary explorer, but an emissary to the frontier of the solar system, tasked with probing the vast and little understood environment that lies between the planets and the stars. NASA formally renamed this new phase the Voyager Interstellar Mission. This transition wasn't sudden. Even as Voyager 2 was photographing Neptune's storms and Triton's geysers, its instruments had been quietly monitoring the plasma, cosmic rays, and magnetic fields of interplanetary space. These measurements were crucial for understanding the heliosphere, the bubble created by the sun's solar wind that envelops the entire solar system. The spacecraft now had the freedom to devote itself fully to this task. With no more planetary flybys to plan, mission controllers could focus on maximizing the scientific return from the spacecraft's long cruise outward. The interstellar mission was, in some ways, more challenging than the planetary phase. By the early 1990s, Voyager 2 was already more than 4.5 billion kilometers, nearly 3 billion miles from Earth, and the distance was increasing every day. At such ranges, radio signals took over 4 hours to travel one way, making real-time control impossible. Commands had to be carefully constructed and uploaded in advance, and the faint signals returning from the spacecraft required the most sensitive antennas of NASA's deep space network to detect. The spacecraft itself was aging too. By the time it left Neptune, Voyager 2 had been operating for nearly 12 years, far longer than its original mission plan of 5. Its plutonium-powered generators were slowly producing less and less electricity as the radioactive fuel decayed. Engineers began a careful program of power management, shutting down non-essential systems and rotating which instruments could run at any given time. It was a slow triage process that would continue for decades, always balancing the need for science with the need to keep the spacecraft alive. Despite these challenges, Voyager 2 remained healthy and productive. Its instruments continued to measure the density and temperature of the solar wind, detect cosmic rays streaming in from distant galaxies, and map the structure of the sun's magnetic field as it stretched outward into space. Each piece of data provided a clue to the size, shape, and behavior of the heliosphere, a region that scientists had only theorized about before. The Voyager interstellar mission was also about endurance and patience. Unlike the dramatic planetary flybys that yielded thousands of pictures and headlines overnight, the interstellar mission was a marathon of slow, incremental progress. Discoveries unfolded gradually as the spacecraft moved into regions never before visited. Scientists compared it to dipping a thermometer into the ocean as a ship sails across the seas. Each reading was small, but together they built a map of uncharted waters. In the public imagination, this new phase gave Voyager a different kind of mystique. The images of Jupiter's storms and Saturn's rings had been dazzling, but now the spacecraft's mission took on a quieter, more philosophical tone. Voyager was heading into the deep dark, carrying not just scientific instruments, but also the Golden Record, a time capsule of Earth's music, languages, and images meant for any intelligent beings who might one day encounter the spacecraft. The idea of a human-made object traveling forever among the stars gave Voyager an almost mythic aura, one that captured imaginations well beyond the scientific community. NASA understood this symbolic power and embraced it. Press releases about Voyager emphasized not only the technical achievements, but also the poetic dimension of the mission. The spacecraft had become humanity's farthest traveling emissary, a tiny but persistent presence reaching into interstellar space. Its continued health and productivity in the early 1990s were seen as a triumph of engineering and a testament to the vision of those who had designed it 2 decades earlier. As Voyager 2 pressed outward, its twin, Voyager 1, was already further ahead on its own interstellar trajectory. The 2 spacecraft, launched within weeks of each other in 1977, had taken different paths, Voyager 1 skipping Uranus and Neptune in favor of a faster trajectory, and Voyager 2 completing the full grand tour. Now, both were heading into the outer reaches, offering 2 vantage points on the heliosphere's distant frontier. The data they sent back together provided scientists with a kind of stereoscopic view of the solar system's boundary with interstellar space. This shift to interstellar exploration ensured that the Voyager mission would remain scientifically relevant long after the planetary encounters had ended. Each year brought the spacecraft closer to the edge of the heliosphere, and each transmission carried data that had never before been available. The planetary chapter had been dramatic and visible, but the interstellar chapter promised discoveries that were subtler, slower, and in some ways even more profound. The heliosphere is one of the most fascinating and least understood features of our solar system. Shaped by the solar wind, it is a vast bubble of charged particles and magnetic fields that surrounds the planets, asteroids, comets, and everything else bound to the sun's influence. For decades before the Voyager missions, scientists had theorized its existence, but its precise size, shape, and behavior were uncertain. Voyager 1 and Voyager 2, as they drifted ever farther from the sun, became the first instruments capable of directly sampling this boundary region. The solar wind is the driver of the heliosphere. This continuous stream of high-energy particles flows outward from the sun in all directions, carrying with it the sun's magnetic field. As the solar wind expands, it pushes back against the interstellar medium. the thin soup of gas, dust, and cosmic rays that fills the space between stars. Where the pressure of the solar wind and the pressure of the interstellar medium balance, a boundary forms. Inside lies the heliosphere. Outside lies interstellar space. The Voyagers carried instruments designed to measure the properties of this solar wind. By the 1990s, as Voyager 2 moved beyond the orbit of Neptune, the readings began to reveal subtle changes. The solar wind was weakening, its density dropping as the spacecraft approached the distant frontier. At the same time, the spacecraft recorded increasing levels of galactic cosmic rays, the high-energy particles that originate outside the solar system. These competing measurements suggested that Voyager 2 was approaching a transition zone, a region where the influence of the Sun gradually waned. Scientists had given names to the predicted layers of this frontier. The termination shock was the first, where the solar wind slowed from supersonic to subsonic speeds as it began to encounter resistance from the interstellar medium. Beyond that lay the heliosheath, a turbulent zone of slowed and heated solar wind. Farther still was the heliopause, the outer boundary of the heliosphere, where the solar wind's influence finally yielded to the galaxy beyond. The Voyagers were destined to traverse each of these regions, but no one knew exactly how far away they were. The data from Voyager 2 was eagerly analyzed for signs of these boundaries. Even small fluctuations in particle counts or magnetic field strength could hint at where the spacecraft was in relation to the heliosphere's edge. It was like trying to detect the presence of a shoreline by listening for faint changes in the sound of the surf. Each measurement brought scientists closer to answering questions that had lingered for decades. How large is the heliosphere? Does it shield Earth and the planets from cosmic radiation? What does the transition into interstellar space actually look like? The importance of the heliosphere extended beyond pure curiosity. The bubble acts as a kind of shield, deflecting a significant portion of galactic cosmic rays that would otherwise bombard Earth and other planets. Understanding its size and effectiveness had implications for everything from space travel to climate science. If astronauts were ever to venture beyond the protective cocoon of the heliosphere, they would be exposed to radiation levels far higher than those experienced within. Knowing the structure of the heliosphere was therefore critical for long-term human exploration of space. Voyager 2's measurements also contributed to models of how stars interact with their galactic environment. The Sun is just one of billions of stars in the Milky Way, each producing its own stellar wind and carving out its own protective bubble. By studying our heliosphere in detail, scientists could make inferences about similar structures around other stars, helping to build a picture of the galaxy as a patchwork of overlapping stellar domains. The heliosphere also took on symbolic importance in the Voyager story. If the planetary flybys had marked humanity's first close-up look at distant worlds, then crossing the heliosphere would symbolize our first true step into interstellar space. It was a natural extension of Voyager's role as a boundary crosser, always venturing into new domains. Scientists and the public alike waited with anticipation for the moment when Voyager 1 or Voyager 2 would finally cross the heliopause and send back the first direct evidence of what lies beyond. By the late 1990s and early 2000s, the Voyagers were still decades away from that final boundary, but their steady progress allowed scientists to refine their theories. Each piece of data, whether it confirmed or contradicted expectations, added another brick to the growing edifice of heliophysics. In this sense, the interstellar mission was as revolutionary as the planetary one. Where the first phase had revealed alien landscapes, the second was revealing the invisible architecture of our cosmic neighborhood. The heliosphere may be invisible, but its importance cannot be overstated. It is the Sun's extended influence, the bubble in which all of human history has unfolded. Voyager's journey toward its edge was not only a scientific mission, but also a philosophical one, probing the literal boundary between home and the wider universe. Voyager 1 and Voyager 2 may have been launched only weeks apart, but their journeys through the solar system and beyond have been distinct, shaped by their different trajectories and the decisions made by mission planners. Together, they tell a story of twin explorers on divergent paths, each contributing unique discoveries that, when combined, give us a fuller picture of the sun's outer frontier and the vastness beyond. Voyager 1 took a more direct route outward after its encounters with Jupiter and Saturn. Its flybys were carefully planned to maximize imaging opportunities and gravitational assists. But once those objectives were complete, it was steered on a path that would carry it above the plane of the solar system. This trajectory allowed it to leave the planetary region more quickly than its sibling, heading almost straight toward interstellar space. As a result, Voyager 1 became the first spacecraft to cross the heliopause in 2012, more than 3 decades after launch. Voyager 2's path was longer and more circuitous, but it was also scientifically richer in terms of planetary exploration. Unlike its twin, Voyager 2 had the opportunity to conduct close flybys of all 4 outer planets: Jupiter, Saturn, Uranus, and Neptune. Each encounter revealed unprecedented details about the giant worlds and their moons, greatly expanding humanity's knowledge. This extended itinerary meant that Voyager 2 would take longer to reach the edge of the heliosphere, but it also meant its contribution to planetary science was unmatched. The different trajectories of the 2 spacecraft also gave scientists an invaluable opportunity to sample different regions of the heliosphere. Voyager 1 moved out of the northern hemisphere of the solar system, while Voyager 2 traveled through the southern hemisphere. By comparing the data from the 2, researchers could begin to understand the heliosphere not as a simple sphere, but as a complex and dynamic structure that might be distorted by external galactic forces. When Voyager 1 crossed the heliopause in 2012, it did so in a sudden and dramatic fashion. Its instruments recorded a sharp increase in galactic cosmic rays and a corresponding drop in solar particles. The magnetic field direction, however, did not change as much as expected, leading to debates among scientists about whether the spacecraft had truly entered interstellar space. Some argued it was in a transition zone rather than fully beyond the sun's influence. Voyager 2's crossing in 2018 provided a valuable point of comparison. Its instruments recorded a similar pattern of changes, but with clearer confirmation of entry into interstellar space. Together, the 2 crossings gave scientists confidence that humanity had indeed set foot, metaphorically speaking, into the galaxy beyond. The timing of the 2 crossings also highlighted the importance of solar activity in shaping the heliosphere. The sun's 11-year cycle of magnetic activity and solar wind variations affects the size of the heliosphere, pushing its boundaries outward or pulling them inward. That Voyager 1 and Voyager 2 crossed at different times during this cycle helped researchers understand how dynamic the heliopause can be, expanding and contracting like the breathing of a giant cosmic lung. While their destinations differ, both spacecraft continue to contribute to science in complementary ways. Voyager 1, heading north of the ecliptic plane, is sending back data about interstellar plasma and cosmic rays. Voyager 2, heading southward, is doing the same, but from a different vantage point. The dual perspectives allow for a kind of stereoscopic vision of interstellar space, adding depth to what might otherwise be a flat or incomplete picture. The story of the Voyagers is not just one of 2 machines, but of how diversity in exploration yields stronger results. If only one probe had been launched, our understanding of the solar system's edge and the interstellar medium would be much more limited. With 2, we can compare and contrast, testing theories against 2 sets of experiences. It is a reminder of the value of redundancy and variety in exploration, qualities that have defined not just the Voyager mission, but human curiosity as a whole. Today, as both spacecraft continue on their divergent paths, they embody different aspects of the same mission. Voyager 1 is the trailblazer, the first to step into the unknown. Voyager 2 is the chronicler, the explorer who took the long road, pausing to observe more of the sights along the way. Together, they represent a dual legacy, two voices in the cosmic wilderness, echoing back to Earth the story of humanity's first interstellar steps. When Voyager 1 and Voyager 2 crossed into interstellar space, they entered an environment dominated not by the solar wind, but by galactic cosmic rays and the faint whispers of material between the stars. This region, while unimaginably empty by human standards, is far from featureless. It is shaped by subtle but powerful forces, and the Voyager spacecraft have provided humanity with its first direct measurements of what might be called the weather of interstellar space. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that zip through the galaxy at nearly the speed of light. They originate from powerful astrophysical events such as supernova explosions, black hole jets, and other cataclysmic processes. For decades, astronomers had studied cosmic rays indirectly, detecting them as they slammed into Earth's atmosphere or as they were deflected by the sun's magnetic field. But the Voyagers offered something no Earth-based instrument could: direct sampling of these particles far beyond the influence of the solar wind. The data collected by Voyager 1 after it crossed the heliopause in 2012 showed a dramatic rise in the intensity of cosmic rays, confirming predictions that the heliosphere had been shielding the inner solar system from much of this radiation. Voyager 2's crossing in 2018 confirmed the pattern, though the exact levels and timing differed slightly, demonstrating that cosmic rays are not uniformly distributed. These differences provided scientists with vital clues about how galactic particles interact with the sun's protective bubble. Cosmic rays pose a double-edged challenge. On one hand, they are a key scientific probe, carrying information about violent astrophysical processes from across the galaxy. On the other, they represent a hazard for future human explorers. Prolonged exposure to high-energy radiation can damage both biological tissue and electronic equipment. The Voyager spacecraft, though far less vulnerable than humans, have experienced occasional glitches, likely caused by cosmic ray hits on their delicate electronics. These events are reminders that interstellar space is a harsh environment, indifferent to human technology. But cosmic rays are only part of the story. The Voyagers have also been studying interstellar plasma, the thin soup of charged particles that fills the void between stars. Though far less dense than the solar wind, interstellar plasma carries information about the magnetic fields that weave through the galaxy. Voyager 1, equipped with a plasma wave instrument, has detected faint oscillations in this medium, like the ripples of a far-off storm spreading across a calm sea. These measurements are helping scientists understand how the interstellar medium interacts with the heliosphere, and by extension, how stars in general carve out protective bubbles in the galaxy. One of the surprising results has been the complexity of the boundary between the heliosphere and interstellar space. Rather than a clean line, the transition appears more like a turbulent mixing zone, with pockets of solar and interstellar material intermingling. Voyager data suggests that magnetic fields play a significant role in shaping this boundary, twisting and draping in unexpected ways. This has implications not just for our solar system, but for astrophysics as a whole, since every star has its own bubble, and together these bubbles form a patchwork across the galaxy. The concept of interstellar weather emerges from these findings. Just as Earth's atmosphere experiences storms, winds, and changing conditions, so too does interstellar space, albeit on vastly different scales. Magnetic turbulence, density fluctuations, and shock waves from distant supernovae all contribute to a dynamic environment. The Voyagers, by drifting through this realm, have become weather stations in the cosmic wilderness, recording subtle shifts that help researchers piece together the larger picture. These measurements also feed back into our understanding of Earth's environment. Cosmic rays, for instance, may influence cloud formation and climate in ways that are not yet fully understood. By providing baseline data on cosmic ray intensity outside the heliosphere, The Voyagers allow scientists to better gauge how much the sun modulates this radiation before it reaches Earth. Such knowledge deepens our appreciation for the protective role the sun plays, while also hinting at the vulnerability of our planet to galactic forces far beyond our control. For space exploration, the implications are practical as well as scientific. Any long-duration crewed missions beyond Earth's magnetic shield, such as trips to Mars or deeper into the solar system, will have to contend with the relentless assault of cosmic rays. The Voyager findings underscore the need for advanced shielding, radiation-hardened electronics, and perhaps even new approaches to spacecraft design. By experiencing interstellar weather firsthand, the Voyagers are helping engineers anticipate the challenges of humanity's future journeys. Perhaps the most profound lesson of this chapter in the Voyager saga is that space is not a void, but a medium. Even in the most remote reaches between stars, there are currents, particles, and fields shaping the environment. What once seemed like empty nothingness is now revealed to be an active, dynamic realm. The Voyagers, drifting silently through this expanse, remind us that the galaxy is alive with motion, and that by listening carefully, we can begin to understand the subtle rhythms of the universe itself. As the years turned into decades, one of the most striking qualities of the Voyager mission became its solitude. Both spacecraft are now so far away that no other human-made object can claim companionship. They are drifting through a region of space that no future mission will likely reach for many decades, if not centuries. This isolation has turned them into symbols of both the vastness of the universe and the extraordinary reach of human ingenuity. Voyager 1, the most distant spacecraft, communicates with Earth from over 24 billion kilometers, about 15 billion miles, away. Voyager 2 trails slightly behind at more than 20 billion kilometers, around 12.5 billion miles. At these distances, the signals they send back take more than 20 hours to cross the gulf of space at the speed of light. By the time a command from Earth reaches them and a response returns, nearly 2 days have passed. This delay alone underscores just how lonely their journeys have become. The faintness of the signals adds to this sense of distance. Each spacecraft transmits with a power output of about 20 watts, less than a typical refrigerator light bulb. Yet thanks to the enormous antennas of NASA's deep space network scattered across Earth, these whispers from the edge of the sun's influence are still captured and interpreted. The fact that humanity can communicate with such distant travelers is itself a marvel of engineering, but it also emphasizes how tenuous the connection has become. The further they drift, the weaker their voices grow, and one day, inevitably, those voices will fade entirely. This isolation is not just physical, but symbolic. Unlike rovers on Mars or orbiters circling Jupiter and Saturn, the Voyagers are not part of a fleet of active spacecraft in the same region. There are no successors following behind them to continue the work in interstellar space. Each probe is alone in its hemisphere, slowly moving outward into the unknown. They represent not only the frontier of exploration, but also a kind of cosmic solitude, where human technology exists, but human presence does not. There is also the psychological impact of their remoteness. For the scientists and engineers who still work with the data, the Voyagers have become more than machines. They are companions in a grand journey, and each signal received feels like a heartbeat confirming their survival. But everyone knows that time is running out. The nuclear power sources that keep their instruments running are slowly decaying, and within the next decade, most, if not all, of their instruments will be turned off to conserve power. Eventually, even their transmitters will fall silent. When that day comes, Voyager 1 and Voyager 2 will continue drifting, but their solitude will deepen, unbroken by any further contact with the world that created them. Their loneliness also highlights the limitations of human exploration. For all our technological brilliance, we have managed to send only 2 probes into interstellar space. They travel at tens of thousands of kilometers per hour. blazing fast by human standards, but glacially slow on a cosmic scale. Even at these speeds, it would take Voyager more than 70,000 years to reach the nearest star, Proxima Centauri, if it were heading in that direction. This sobering reality forces us to confront the immensity of the cosmos and the challenges of traveling within it. Yet their solitude is not without meaning. Because they are alone, every bit of data they send is precious, irreplaceable. They are pathfinders into a region no other spacecraft has entered. Their journeys remind us that exploration is often a solitary endeavor, carried out by pioneers who go first into uncharted territory. Just as ancient explorers once set sail across oceans without knowing if they would ever return, the Voyagers push into the cosmic sea, alone but for the faint connection to their home planet. The loneliness of the Voyagers also resonates with people in a deeper way, beyond science. Many see them as metaphors for the human condition, small, fragile, and isolated in an immense and indifferent universe. And yet, like the spacecraft, humanity continues to send its voice outward, refusing to be silent. The golden records on board carry music, greetings, and images of Earth, a symbolic effort to bridge the void, to say we were here and we wanted to be known. In this way, the Voyagers transform their solitude into something profound, a message in a bottle cast into the galactic ocean. Even as their instruments eventually shut down, the spacecraft themselves will endure. They are expected to continue drifting among the stars for billions of years, long after Earth is gone and the sun is faded. Their loneliness will become eternal, but so too will their testimony. They will be silent witnesses to the life cycle of the galaxy, carrying with them the story of a species that once looked outward and dared to reach. In their isolation, the Voyagers show us both the fragility and the resilience of human exploration. They may be alone, but they are also immortal, carrying the hopes and voices of Earth into a universe that may one day listen. Their loneliness is profound, but it is also beautiful, for it embodies the very essence of exploration, to leave the familiar behind and to journey where no one has gone before, even if it means going alone. Communicating with the Voyager spacecraft is one of the most impressive technical feats of the mission, and it grows more remarkable with every passing year. The spacecraft are now so far away that their signals are almost unimaginably faint. Yet despite the vast distances, we can still hear their voices, though it requires extraordinary precision, patience, and engineering. The Voyagers send data back to Earth using radio signals transmitted by their high-gain antennas. When they were launched in 1977, the distances involved seemed almost unthinkable. But mission planners knew that as the spacecraft traveled farther from Earth, their signals would weaken according to the inverse square law. By now, more than 20 billion kilometers, over 12 billion miles from Earth, those signals have faded to a whisper. To put it into perspective, the power of the radio signal received on Earth from the Voyagers is less than a billionth of a watt, far weaker than the energy of a single snowflake hitting the ground. Catching such faint signals requires one of the most sophisticated communication systems ever built. NASA's Deep Space Network. This system consists of giant radio antennas located in California, Spain, and Australia, positioned around the globe so that at least one is always in contact with the spacecraft as the Earth rotates. The largest of these dishes are 70 meters, about 230 feet across, and they are tuned to detect the faintest radio whispers from the cosmos. Without them, communication with the Voyagers would have been lost long ago. But distance is only part of the challenge. Time delay also plays a critical role. A signal from Voyager 1 now takes more than 22 hours to reach Earth, and the reply takes just as long to go back. This means that any command sequence sent to the spacecraft requires careful planning, as engineers must wait nearly 2 days to confirm whether it executed properly. Quick fixes or real-time adjustments are impossible. Every action is deliberate and painstaking. Another challenge lies in the aging technology aboard the spacecraft. Voyager's systems are based on electronics from the 1970s, with computer memory measured in kilobytes rather than gigabytes. Commands must be crafted with extreme care, making the most of limited resources and ensuring compatibility with hardware that has been operating far beyond its expected lifespan. The spacecraft used digital tape recorders and old-style radio transmitters, yet they continue to work reliably thanks to careful management from Earth. The communication link has also been tested by occasional malfunctions. In 2023, for instance, Voyager 2 briefly fell silent after a command error caused its antenna to point slightly away from Earth. For several weeks, no signal was received, raising fears that contact might be permanently lost. But engineers eventually managed to re-establish the connection, using the Deep Space Network to send a carefully timed command. Moments like this are a stark reminder of the fragility of the link, but they also showcase the skill and dedication of the mission teams who continue to nurse these aging spacecraft. Power management adds another layer of difficulty. As the radioisotope thermoelectric generators slowly lose output, the mission team must prioritize which instruments to keep running. Each choice impacts the type of data the Voyagers can send back, and eventually, even the transmitters themselves will lack the power to operate. Engineers estimate that sometime in the early 2030s, communication will cease entirely. Until then, every transmission received is treasured, like the final chapters of a long and extraordinary story. Despite these obstacles, the Voyagers remain among the most productive scientific missions ever launched. Their ability to send data across such staggering distances is a testament to the ingenuity of the Deep Space Network and the durability of the spacecraft themselves. More than that, their continued communication is symbolic, a fragile but unbroken thread connecting humanity to its most distant emissaries. What makes this communication especially poignant is its one-way nature in the long run. Eventually, the Voyagers will outlast our ability to hear them. They will keep drifting outward, antennas still pointing at Earth, but their voices too faint to detect. In that silence, the spacecraft will continue their journeys, no longer reporters but still representatives of humanity, carrying our message into the stars. For now, however, they still speak and we still listen. Each faint signal is a reminder that across billions of kilometers of empty space, human-made machines are out there, alive with data, reaching across the void. It is one of the most extraordinary examples of human persistence to design, launch, and maintain a line of communication with objects that have left the solar system. The Voyager communication link is not just a technical achievement. It is a thread of connection between Earth and the cosmos, one that underscores the depth of our curiosity and the lengths to which we will go to satisfy it. Every spacecraft has a lifespan defined by its power supply, and the Voyagers are no exception. From the very beginning, mission planners knew that the greatest limitation on how long the spacecraft could function would not be fuel or structural failure, but the slow decline of their nuclear batteries. More than 4 decades later, the dwindling power of these generators is the ticking clock that defines the final chapter of the Voyager missions. Both Voyager 1 and Voyager 2 are powered by radioisotope thermoelectric generators, or RTGs. These devices use the heat produced by the natural decay of plutonium-238 to generate electricity. At launch in 1977, each spacecraft's RTGs provided about 470 watts of power, enough to run their instruments, communication systems, and heaters. But plutonium-238 has a half-life of about 88 years, meaning the heat it produces declines slowly but steadily over time. Today, each Voyager has less than half of its original power output, and that number continues to shrink each year. As the available power decreases, mission engineers have had to make difficult decisions about which instruments to keep running and which to shut down. The process has been gradual, stretching over decades, but every few years another system is turned off in order to keep the most vital instruments alive. Cameras were among the first to go, deactivated after the planetary. Encounters were complete to save power. More recently, heaters have been shut down one by one, leaving some instruments operating in conditions far colder than they were ever designed to withstand. Incredibly, many continue to function, a testament to the robustness of 1970s engineering. The power limits also affect communication. Transmitting a signal back to Earth requires a significant amount of electricity, and as the RTGS weaken, the transmitters themselves will eventually become unsustainable. This will mark the true end of the mission, not when the spacecraft break down, but when they can no longer speak to us across the void. Engineers expect this to happen sometime in the early 2030s, though the exact timing depends on how carefully power is rationed in the coming years. In the meantime, each decision about which systems to shut down carries scientific consequences. Shutting off a plasma instrument, for example, means losing data about interstellar currents. Turning off a magnetometer reduces our ability to map cosmic fields. Every sacrifice narrows the spacecraft's vision, and yet the team has managed to preserve an extraordinary stream of science by balancing the trade-offs with meticulous care. Each year of continued operation is a victory. There is also a philosophical weight to the countdown. The Voyagers have been part of human culture for so long that the thought of their eventual silence carries an emotional resonance. They are not just machines, but symbols of exploration, endurance, and human curiosity. As each instrument falls quiet, it feels like a dimming of one of the last lights in the farthest reaches of the cosmos. The engineers managing the mission are keenly aware of this, and their work to stretch the power supply reflects both scientific dedication and a deep respect for the spacecraft's legacy. Still, the inevitable end does not diminish what the Voyagers have achieved. When their transmitters finally go silent, they will not cease to exist or to matter. They will continue drifting through the galaxy, intact and enduring, carrying their golden records in the story of Earth. They will become silent ambassadors, beyond contact but still meaningful. Their endurance already defies expectations. Any years they continue to operate from now on are a gift, extending a mission that was only designed to last 5 years at the start. The countdown also offers lessons for future interstellar missions. Engineers are studying how long the Voyager systems have lasted without maintenance, and how the RTGs have performed after decades in space. These insights will inform the design of new probes, ensuring that humanity's next steps into interstellar space are even more durable and capable. In this way, the Voyager's slow decline is not an ending, but a passing of the torch to the missions that will follow. For now, as long as their voices continue to reach us, the Voyagers remain active participants in humanity's story of exploration. The final countdown is underway, but every extra year, every faint signal, every packet of data adds to a legacy that is already unmatched. The ticking clock of their power supplies is not just a reminder of mortality, it is also a reminder of how far we have come and how much these two small machines have given us. Among the most iconic features of the Voyager spacecraft is something that has nothing to do with their scientific instruments or engineering design. Bolted to the side of each spacecraft is the Golden Record, a phonograph record plated in gold that serves as a time capsule of Earth. Unlike the scientific instruments, which were designed to collect data for humans back on Earth, the Golden Record was created for any beings who might one day encounter the spacecraft in the distant future. It is part science, part art, part philosophy, and entirely symbolic of humanity's desire to reach beyond itself. The idea of including a message for extraterrestrials was not new. Earlier missions, such as Pioneer 10 and 11, carried engraved plaques with simple line drawings of humans, the spacecraft, and the position of the sun relative to nearby pulsars. But the Voyager Golden Records were far more ambitious. Instead of a static image, they were designed to carry sounds and images of Earth, pressed into a format that could, in theory, be played back by any intelligent species able to decipher the instructions included with the record. Each record contains 115 images encoded in analog form, a selection of natural sounds, like thunder, birdsong, and whale calls, greetings spoken in 55 different languages, and 90 minutes of music from cultures around the world. The music ranges from classical works by Bach and Beethoven to traditional folk songs from across continents. It even includes Chuck Berry's Johnny B. Goode, a nod to the rise of rock and roll. The selection was curated by a team led by Carl Sagan, who sought to represent not only the diversity of human culture, but also the beauty and universality of music and sound. The Golden Record also includes a printed message, inscribed on its cover, explaining how to play it. Using simple diagrams, it shows how to build a stylus and how to interpret the patterns of grooves into images and sounds. The diagrams reference hydrogen atoms, the most common element in the universe, as a kind of universal Rosetta Stone, ensuring that the instructions would be comprehensible to any advanced species. The cover even includes a pulsar map, similar to the Pioneer plaques, to indicate Earth's position in the galaxy. The purpose of the Golden Record was never practical. No one expected that extraterrestrials would actually find and play the records, given the vastness of space and the infinitesimal chance of encounter. Instead, the project was symbolic, a gesture of goodwill, a declaration that Earth had reached out to the stars. It was an acknowledgement that humanity is part of a much larger universe, and that even as we explore, we also want to be known. For many, the Golden Record is the most poetic aspect of the Voyager mission. The spacecraft are not just instruments of science, but carriers of culture, art, and identity. They represent humanity not only as a technological species, but as one that creates music, shares stories, and values beauty. The decision to include whale songs alongside Beethoven and greetings from children alongside photographs of cities reflects an effort to present Earth in its full richness and complexity. The legacy of the Golden Record has been profound. It has inspired countless artists, musicians, and writers who see in it a symbol of hope and connection. It has been referenced in novels, films, and documentaries, becoming one of the most enduring cultural touchstones of the space age. Its existence has even sparked philosophical debates about what it means to represent humanity. Which cultures, languages, and music should be included? What aspects of Earth do we highlight, and which do we leave out? These questions reveal as much about us as the record itself. The Golden Record also resonates because of the contrast between its message and the spacecraft carrying it. The Voyagers are hard, utilitarian machines, built for scientific precision and endurance. Yet strapped to their sides is a delicate record filled with laughter, music, and the sounds of nature. It is as if a scientific instrument has been given a soul, a reminder that exploration is not just about data, but about meaning. One day, billions of years from now, the Voyagers will still be traveling among the stars, long after Earth and the Sun have changed beyond recognition. By then, the Golden Records will be ancient relics, perhaps the only surviving trace of human civilization. Whether or not they are ever found, their presence ensures that humanity has left a mark on the galaxy. They are our greeting cards to eternity, hopeful, fragile, and deeply human. In many ways, the Golden Records may outlast the science they were sent to accompany. The instruments will fail, the signals will fade, and the data will be archived. But the records will continue their silent journey, carrying with them the story of who we were when we first ventured beyond the solar system. In that sense, their legacy is not measured in discoveries, but in inspiration, reminding us that exploration is as much about identity as it is about knowledge. Few space missions have managed to capture the public's imagination quite like the Voyagers. While many robotic spacecraft have produced spectacular discoveries, the Voyagers stand apart as cultural icons, woven into the fabric of popular imagination in a way that transcends science. They are not only machines of exploration, but symbols of humanity's curiosity, resilience, and yearning for connection with the cosmos. From the very start, the Voyager mission generated headlines. The images of Jupiter and Saturn in the late 1970s and early 1980s were broadcast on television, appearing in newspapers and magazines around the world. For the first time, people could see the swirling storms of Jupiter in detail, the icy rings of Saturn, and the strange volcanic surface of Io. The sense of discovery was palpable, and the public followed the spacecraft as if they were explorers in a great interplanetary adventure. As time went on, the Voyagers became more than just scientific missions. They began to symbolize the endurance of exploration itself. Each milestone, the flybys of Uranus and Neptune, the family portrait of the solar system, the pale blue dot photograph, was not just a scientific achievement but a cultural moment. Carl Sagan, who served as one of the mission's leading advocates, was instrumental in shaping this narrative, framing the Voyagers as emissaries of Earth and interpreters of cosmic perspective. His poetic reflections ensured that the missions were not remembered only for their data, but also for their meaning. Popular culture embraced the Voyagers in countless ways. The spacecraft have been referenced in films, novels, television shows, and music. They inspired episodes of Star Trek, were featured in documentaries like The Farthest, and became the subject of books, plays, and even art installations. The Golden Record, in particular, has become a touchstone for creativity, inspiring musicians to reinterpret its contents and artists to reflect on its significance. For many, the very idea that Chuck Berry, whale songs, and greetings in dozens of languages are now flying through interstellar space is irresistible. The Voyagers also entered the realm of philosophy and spirituality. The pale blue dot image, taken by Voyager 1 at Sagan's urging, became a powerful symbol of human humility. In his famous reflection, Sagan described Earth as a pale blue dot suspended in the cosmic dark, reminding us of the fragility of our world and the need to cherish it. This single image has had a cultural impact far beyond the mission itself, becoming one of the most quoted and shared reflections in discussions of space, humanity, and our place in the universe. The endurance of the spacecraft has also contributed to their cultural status. They were launched in the disco era of the 1970s, but they continue to operate well into the 21st century, bridging generations. For people who watched their launch, the Voyagers are reminders of the optimism and ambition of that time. For younger generations, they are proof that exploration can endure across decades, long after the engineers who built them have retired. In this way, the Voyagers have become timeless, linking past, present, and future. Social media has given the Voyagers a new voice in recent years. NASA's accounts for the spacecraft share updates and milestones in ways that personify them, treating the Voyagers almost like characters with personalities. This has deepened the sense of connection many people feel, as though the spacecraft are not just machines, but fellow travelers reporting back from the edge of the unknown. The emotional resonance of these updates is striking. People celebrate their achievements, mourn their struggles, and brace for the day when the signals finally fade. Beyond entertainment and inspiration, the cultural impact of the Voyagers reflects something fundamental about human identity. The spacecraft are reminders that we are explorers at heart, unwilling to remain confined to our planet. They embody our drive to push outward, to learn and to connect. Even as they drift alone in the dark, they remain tethered to us by meaning and memory. Their place in popular imagination shows that space exploration is not just about science. It is about stories, symbols, and shared dreams. The Voyagers' presence in culture also ensures that their legacy will endure long after their signals cease. They will not vanish into obscurity, but remain part of humanity's collective narrative. As long as people tell stories about exploration, the Voyagers will be there. Two small spacecraft that became larger than life, not because of their size or speed, but because of what they represent. When Voyager 1 swept past Jupiter, the gas giant itself was not the only spectacle. the spacecraft was able to capture unprecedented details of the Galilean moons, those 4 large satellites that Galileo first observed in 1610. Before Voyager's close approach, these worlds were little more than bright dots seen through telescopes, their surfaces largely a mystery. Voyager 1 transformed them into real places, each one unique, each one offering a story about the solar system's history. Io, the innermost of the Galilean moons, was expected to be a battered, cratered rock, much like Earth's moon. Instead, Voyager revealed it to be the most volcanically active body in the solar system. Images showed towering plumes of sulfur and volcanic material erupting into space, some rising hundreds of kilometers above the surface. These eruptions were proof of powerful internal heat, driven by tidal forces exerted by Jupiter's immense gravity and the gravitational interplay with its neighboring moons. Io's surface was constantly being resurfaced, giving it an otherworldly appearance, painted in yellows, reds, and whites from sulfur compounds. Europa, just beyond Io, stunned scientists in a completely different way. Rather than being covered in craters, its smooth, icy shell was crisscrossed by long, dark lines and ridges. The lack of craters suggested that its surface was relatively young, and the patterns hinted at movement within the ice. This led to one of Voyager's most profound legacies, the suspicion that beneath Europa's icy crust might lie a vast subsurface ocean, kept liquid by the same tidal heating that drives Io's volcanoes. That possibility set the stage for decades of scientific fascination and exploration plans, as liquid water is a prime ingredient for life. Ganymede, the largest moon in the solar system, appeared as a mix between the ancient and the renewed. Voyager showed terrains marked by dark, heavily cratered regions alongside lighter grooved terrains shaped by tectonic activity. These contrasting surfaces hinted at a complex geological history, one that suggested Ganymede had once been far more active. Its sheer size, larger even than Mercury, added to its intrigue as a kind of miniature planet orbiting a planet. Callisto, the outermost of the 4, offered yet another surprise. Its heavily cratered landscape looked ancient and unchanging, scarred by impacts stretching back billions of years. Yet Voyager detected subtle variations in the terrain, suggesting that even this seemingly frozen relic had experienced geological processes. The images and data from Voyager 1's encounter with Jupiter's moons showed the extraordinary diversity of planetary bodies orbiting just one giant planet. Each moon challenged assumptions, reshaped scientific theories, and expanded humanity's imagination about what worlds could look like and how they could evolve. For the first time, scientists realized that moons could be as fascinating, complex, and dynamic as planets themselves. After its groundbreaking discoveries at Jupiter, Voyager 1 moved on to the next great destination in its path, Saturn. By the late 1970s, Saturn was already famous for its magnificent ring system, but telescopic observations had never been able to reveal the level of detail that Voyager was about to uncover. The spacecraft's flyby in November 1980 marked another watershed moment in planetary science. As Voyager 1 approached Saturn, its cameras captured stunning close-up views of the planet's atmosphere. Saturn's clouds, though more muted in color than Jupiter's, displayed subtle bands and swirls driven by high-speed winds that could reach over 1,800 kilometers per hour. The spacecraft detected atmospheric features such as long-lived storms and wave-like patterns that hinted at deep, turbulent dynamics beneath the surface haze. But the rings quickly became the star of the show. Voyager 1 revealed that Saturn's rings were not solid sheets, but instead made up of countless particles of ice and rock, ranging in size from tiny grains to house-sized boulders. The spacecraft's images showed intricate structures within the rings, gaps, braids, spokes, and ripples, phenomena that scientists had never seen before. These features hinted at the gravitational influence of Saturn's many moons, some of which acted like cosmic shepherds, shaping and maintaining the rings through their orbits. The moons themselves proved to be as fascinating as the rings. Titan, Saturn's largest moon, was a major focus of the mission. Voyager 1 flew close to Titan, but its thick orange atmosphere, rich in nitrogen and hydrocarbons, concealed the surface from view. Even without seeing the ground, the detection of such a dense, Earth-like atmosphere raised tantalizing questions about what lay beneath. Was Titan a frozen wasteland, or did it hide lakes and seas of liquid methane and ethane? This mystery would remain unsolved until later missions, but Voyager's data ensured Titan would become a prime target for future exploration. Other moons also surprised scientists. Mimas, with its enormous Herschel crater, looked like a giant eyeball or a battered Death Star. Enceladus, though only glimpsed from afar, showed a bright, icy surface, leaving hints that it too might have secrets beneath its frozen shell. Rhea, Tethys, and Dione revealed surfaces scarred by craters and fractures, evidence of violent pasts and geological forces. Voyager 1's encounter with Saturn not only enriched scientific understanding, but also had mission-defining consequences. Its close flyby of Titan altered its trajectory, sending it on a path that carried it up and out of the plane of the solar system. Unlike its twin Voyager 2, which continued on to Uranus and Neptune, Voyager 1's journey beyond Saturn marked the end of its planetary encounters. From that point onward, its mission would be the exploration of interstellar space. The Saturn flyby encapsulated what made Voyager so extraordinary. Each destination opened entirely new chapters of knowledge, revealed wonders never before imagined, and left humanity eager for the next question to be answered. While Voyager 1 had already delivered groundbreaking results at Jupiter, Voyager 2 was not to be overshadowed. Launched just a few weeks earlier, Voyager 2 followed a slightly different trajectory and arrived at Jupiter in July 1979, 4 months after its twin's historic flyby. This timing gave scientists an extraordinary opportunity to perform comparative studies, seeing how Jupiter's dynamic system evolved in real time over the course of months. Voyager 2's instruments, still in excellent condition after their long journey, captured the giant planet with fresh eyes. It observed shifting weather patterns in Jupiter's atmosphere, including changes in the Great Red Spot and the emergence of smaller, swirling storms. By comparing Voyager 1's earlier data with its own, Voyager 2 revealed that Jupiter's atmosphere was not static, but constantly changing, with storms that grew, shrank, and drifted across latitudes. The spacecraft also measured lightning storms and auroras, evidence of Jupiter's powerful electrical environment. The flyby gave new insights into Jupiter's faint ring system, which had been discovered only months earlier by Voyager 1. Voyager 2 confirmed its existence and provided additional details on its composition and structure, showing that the rings were composed of dark, microscopic dust rather than the bright ice of Saturn's rings. This discovery fundamentally reshaped ideas about how giant planets form and maintain such features. As Voyager 2 passed by Jupiter's moons, it became clear that each had a personality of its own. Io's volcanoes, first revealed by Voyager 1, were seen again, this time more active than ever. Voyager 2 spotted new eruptions and fresh deposits of sulfurous material, proving that Io's surface was constantly renewing itself. Europa also continued to intrigue. Voyager 2 provided even clearer views of its cracked, icy crust, strengthening the case for a hidden ocean beneath. The other Galilean moons, Ganymede and Callisto, revealed still more surprises. Ganymede's surface appeared to be a strange patchwork of light and dark regions, riddled with grooves that hinted at tectonic or cryovolcanic activity. Callisto, on the other hand, looked older and more battered, covered in ancient craters, suggesting it had remained geologically inactive for billions of years. Voyager 2's flyby didn't just add to Voyager 1's discoveries, it amplified them. With 2 sets of eyes on Jupiter, scientists could piece together a fuller picture of the planet, its atmosphere, its rings, and its moons. This dual perspective demonstrated the enormous scientific value of flying twin spacecraft, as no single mission could have captured such breadth of data. After completing its work at Jupiter, Voyager 2 was set on a course towards Saturn, carrying with it the promise of another spectacular encounter. But while its twin would leave the planetary stage after Titan, Voyager 2 was destined for an even grander tour, one that would extend humanity's gaze to the outermost reaches of the solar system. Voyager 2 reached Saturn in August 1981, nearly a year after Voyager 1's historic flyby. By then, the world had already been dazzled by the first close-up images of Saturn's shimmering rings and the mysterious haze of Titan. Yet Voyager 2's passage was anything but a repeat performance. Its extended mission meant that its flight path and objectives were carefully designed to expand upon Voyager 1's discoveries, filling in gaps, providing longer observation windows, and laying the groundwork for its trajectory deeper into the solar system. Saturn itself revealed even more complexity under Voyager 2's gaze. The spacecraft's cameras captured the planet's cloud bands in greater detail, revealing subtle color variations and storm structures that had previously gone unnoticed. Unlike Jupiter, whose atmosphere boiled with chaotic turbulence, Saturn's atmosphere looked more subdued. But Voyager 2 showed that beneath this calm exterior were fast winds exceeding 1,800 kilometers per hour, or about 1,100 miles per hour, some of the strongest in the solar system. These high-speed winds gave Saturn its smooth pastel appearance, but hinted at a dynamic interior. The true spectacle of the encounter came from Saturn's rings. Voyager 1 had already shown that the rings were far more intricate than expected, but Voyager 2 spent more time observing them, discovering dozens of thin braided ringlets and mysterious radial features that appeared like spokes in a wheel. These spokes, thought to be caused by interactions between tiny dust particles and Saturn's magnetic field, hinted at complex electromagnetic processes at work. Voyager 2 also provided better measurements of ring particle size, density, and distribution, helping to refine theories about how the rings formed and why they persist. Saturn's moons also came under fresh scrutiny. Voyager 2 passed close to Enceladus, revealing a surprisingly bright, reflective surface. The imagery suggested recent resurfacing, an unexpected finding that raised the possibility of internal activity. Decades later, the Cassini mission would confirm that Enceladus harbors a global subsurface ocean and geysers that spew water vapor into space. But Voyager 2 was the first to hint at the moon's dynamic potential. The spacecraft also provided sharper views of Tethys, Dione, and Rhea, each showing heavily cratered surfaces with hints of past geological processes. Hyperion, an oddly shaped moon, was seen as a tumbling object with a sponge-like surface, unlike anything previously encountered. Voyager 2's observations emphasized just how diverse Saturn's family of moons truly was, each body shaped by its own history of impacts, tectonics, and possible internal heating. Titan, Saturn's largest moon, remained frustratingly shrouded. Voyager 2 confirmed what Voyager 1 had seen, a thick orange haze that completely obscured the surface. While the spacecraft's instruments gathered data on its atmosphere, rich in nitrogen with traces of methane, the true nature of Titan's surface remained hidden, a mystery that would persist until the Cassini-Huygens mission in the 2000s. Voyager 2's successful flyby not only enriched humanity's understanding of Saturn, but also positioned the spacecraft for something extraordinary, a gravitational assist that would propel it toward Uranus, making it the first spacecraft in history to encounter that distant ice giant. The extended mission, known as the Grand Tour, was now fully underway, and Voyager 2's discoveries at Saturn were the crucial stepping stones toward exploring the solar system's uncharted outer frontier. In January 1986, Voyager 2 became the first and only spacecraft to visit Uranus, giving humanity its first close look at one of the ice giants. Up to that point, Uranus was little more than a faint green-blue dot in telescopes, a planet known for its odd tilt of nearly 98 degrees, which caused it to roll around the sun on its side. Many scientists doubted the flyby would reveal much. Uranus appeared bland and featureless from Earth. But Voyager 2 proved that even seemingly quiet planets could hold surprises. The spacecraft approached within 81,500 kilometers, about 50,600 miles, of Uranus's cloud tops. From that distance, its instruments uncovered a world with an atmosphere dominated by hydrogen and helium, with a significant fraction of methane giving the planet its blue-green tint. Unlike Jupiter and Saturn, Uranus's atmosphere appeared subdued, with only faint cloud bands and no massive storms dominating the view. This calm exterior suggested a planet with less internal heat driving convection. In fact, Voyager 2's instruments confirmed that Uranus emits very little heat compared to what it receives from the Sun, making it one of the coldest planets in the solar system, with temperatures around minus 224 degrees Celsius, minus 371 degrees Fahrenheit. Despite its muted atmosphere, Uranus revealed an astonishingly complex system of moons and rings. Voyager 2 discovered 10 new moons, raising the total count to 27. Among these were Miranda, Ariel, Umbriel, Titania, and Oberon, the largest moons of Uranus, each named after characters from Shakespeare and Alexander Pope. Miranda, in particular, stunned scientists. Its surface was unlike anything seen before, with giant cliffs, fractured terrain, and patchwork regions that looked stitched together from different epochs of geological history. Some cliffs rose higher than Mount Everest on Earth, suggesting dramatic tectonic upheaval or resurfacing in the moon's past. The rings of Uranus also came into sharper focus. First detected from Earth in 1977, they appeared faint and narrow compared to Saturn's broad, gleaming system. Voyager 2 confirmed at least 11 distinct rings, composed of dark material that reflected very little sunlight. The structure of these rings hinted at shepherd moons, small bodies whose gravitational influence helps maintain the sharp edges of the rings. Perhaps the biggest surprise of the encounter was Uranus's magnetic field. Unlike Earth, Jupiter, or Saturn, Uranus's magnetic field is tilted 59 degrees away from its rotational axis and is significantly offset from the planet's center. This produced a lopsided, twisted magnetosphere that was unlike any seen before. Scientists had not anticipated such an unusual configuration, and the finding forced new models of how planetary dynamos can operate deep inside icy worlds. For all the excitement, Voyager 2's flyby was also limited by timing. The spacecraft arrived at Uranus during the planet's southern solstice, meaning the southern hemisphere was in constant sunlight while the northern hemisphere lay in total darkness. This prevented a full survey of the planet's atmosphere and moons. Still, the brief visit provided a wealth of data and transformed Uranus from a distant curiosity into a world with its own unique identity and puzzles. Voyager 2's successful flyby of Uranus was a triumph of engineering and navigation, showing that a spacecraft launched nearly a decade earlier could still deliver groundbreaking science at the edge of the known solar system. But the mission didn't stop there. With one final major planetary encounter ahead, Voyager 2 set its sights on Neptune, the last unvisited giant planet. Voyager 2's flyby of Uranus was more than just another milestone on its long journey outward. It was a moment that reshaped humanity's perspective on what the outer solar system truly held. Before this encounter, Uranus was a planet mostly ignored, overshadowed by the dramatic storms of Jupiter, the gleaming rings of Saturn, and the mysterious pull of Neptune at the solar system's edge. It was faint, distant, and seemingly unremarkable. Yet in a matter of hours, Voyager 2 revealed a world of strange tilts, fractured moons, and one of the most peculiar magnetic fields in the solar system. The visit to Uranus underscored one of the Voyager mission's greatest lessons. Never assume that a planet will be simple. Uranus had long been considered a quiet, dull world, but instead, it emerged as an enigma. The discovery of Miranda's chaotic surface Omphun challenged geological theories, forcing scientists to reconsider how small, icy moons could sustain such dramatic features. The offset magnetic field suggested internal dynamics that had not been predicted, raising questions about whether other ice giants, like Neptune, might hold similar surprises. The encounter also emphasized the fleeting nature of planetary exploration. Voyager 2's closest approach lasted only a few hours, and then the spacecraft was already speeding away, leaving behind questions that remain unanswered even today. Why is Uranus so cold compared to the other giants? What caused its extreme axial tilt? How exactly did its moons evolve to their present states? And what lies beneath its hazy blue-green clouds? These questions highlight both the achievements and the limitations of a flyby mission. A single visit can transform knowledge, but cannot provide the depth of understanding that comes with long-term observation. From a human perspective, the Uranus encounter was also a reminder of the scale of Voyager's accomplishment. The spacecraft was now more than 2.8 billion kilometers, 1.7 billion miles from Earth, operating flawlessly despite being nearly a decade old. Commands sent from Earth took more than 2.5 hours to arrive, yet the tiny spacecraft responded with precision. The images it sent back had traveled across unimaginable distances, crossing the void to provide Earth with its first intimate views of a planet that had been nothing more than a dot of light for centuries. Perhaps most importantly, Uranus prepared scientists and engineers for what lay ahead. It showed that Voyager 2 could still operate in the harshest conditions, navigating uncharted territories and delivering unexpected science. The encounter provided both confidence and caution. Confidence that Neptune could be reached and studied with equal success, and caution in recognizing that the outer planets were full of surprises waiting to be uncovered. As Voyager 2 continued on its trajectory toward Neptune, Uranus faded back into the darkness, awaiting the day when another spacecraft might one day return. In the meantime, the world now had its first real portrait of the tilted planet, thanks to the little spacecraft that had been designed for a much shorter journey but had exceeded every expectation. In August 1989, Voyager 2 reached the final planet of its journey, Neptune. This encounter was historic not only because it was the first close visit to the distant ice giant, but also because it remains, to this day, the only time a spacecraft has flown by Neptune. After more than a decade in space and billions of kilometers traveled, Voyager 2 was about to close out its planetary mission with a spectacular finale. Neptune had always been an elusive world. Even in the best Earth-based telescopes, it appeared as nothing more than a blurry blue dot. Scientists expected it to be cold, quiet, and perhaps similar to Uranus. Instead, Voyager 2 revealed a planet bursting with activity. Despite receiving only a fraction of the sunlight that Uranus does, Neptune displayed dramatic atmospheric phenomena. The spacecraft's cameras captured images of massive storms, including the now famous Great Dark Spot, a storm system nearly the size of Earth. Nearby, bright white clouds, nicknamed Scooter, zipped around the planet at extraordinary speeds. These storms suggested that Neptune, far from being dormant, had an active and turbulent atmosphere. Voyager 2's instruments measured Neptune's winds as the fastest in the solar system, reaching up to 2,100 kilometers per hour, about 1,300 miles per hour. These supersonic winds tore across the planet's upper atmosphere, raising new questions about how such energy could be sustained in a world so far from the sun. The answer likely lies in Neptune's internal heat, which is stronger relative to its size than Uranus's. While Uranus seems to release little excess heat, Neptune radiates more than twice the amount of energy it receives from the sun, driving the chaotic weather systems Voyager observed. The flyby also offered humanity its first close view of Neptune's moons. Triton, the largest moon, immediately stood out. Voyager 2's cameras revealed a strange, icy surface with cantaloupe-like textures and vast nitrogen ice plains. More astonishingly, the spacecraft observed active geysers erupting from Triton's surface, venting nitrogen gas into space. This made Triton one of the few geologically active moons in the solar system, alongside Io and Enceladus. The retrograde orbit of Triton, moving opposite to Neptune's rotation, suggested it was likely a captured Kuiper Belt object, providing a tantalizing link between Neptune and the icy population of bodies that orbit beyond Pluto. The spacecraft also confirmed the presence of a faint ring system around Neptune, previously detected from Earth but never directly observed. These rings were dark, narrow, and irregular, with clumps and arcs that defied expectations. The discovery reinforced the idea that planetary. Rings were not limited to Saturn, but were instead a common feature among the gas and ice giants. Voyager 2's closest approach brought it within 4,950 kilometers, about 3,080 miles, of Neptune's cloud tops, the tightest flyby of any planet in the mission. The spacecraft then executed a precisely timed trajectory past Triton, using the moon's gravity to slingshot itself out of the plane of the solar system. This maneuver effectively ended Voyager's planetary tour, setting it on a course into interstellar space. The Neptune flyby left a legacy of surprises and mysteries. Why does Neptune generate such extreme winds? What powers Triton's geysers? How stable are its rings and arcs? These questions remain open decades later, fueling calls for future missions to return. Yet even with those unanswered puzzles, Voyager 2's visit gave Neptune an identity far richer and more dynamic than scientists had imagined. It turned the faint blue dot into a world of storms, active moons, and strange rings, ensuring that Neptune would forever stand as a jewel at the solar system's edge. Voyager 2's flyby of Neptune was more than just the end of a planetary tour. It was a curtain call that exceeded every expectation. By the time the spacecraft reached this distant ice giant, there was a sense among many scientists that the grand tour was winding down quietly. After all, Uranus had appeared subdued, and Neptune, even farther from the Sun, was expected to be even less dynamic. Instead, what Voyager 2 revealed in 1989 stunned the world. A planet roaring with storms, winds that outpaced anything else in the solar system, and a moon so geologically alive that it spewed plumes of nitrogen into space. The encounter was also bittersweet. Unlike Jupiter and Saturn, which were later revisited by Galileo and Cassini, and unlike Mars or Venus, which have hosted fleets of orbiters and rovers, Neptune has not been seen up close again since Voyager 2's brief visit. The spacecraft's images and data remain our only detailed look at the planet and its moons, frozen in time more than 3 decades ago. In many ways, Neptune remains one of the least understood of the major planets, and that fact makes Voyager 2's contribution even more valuable. The discoveries raised fundamental questions. The Great Dark Spot, for instance, vanished when the Hubble Space Telescope observed Neptune just a few years later, replaced by new storm systems. This suggested a constantly changing atmosphere, one that likely undergoes cycles still poorly understood. Triton's active geysers were even more surprising. For a moon so far from the Sun, conventional wisdom would predict a frozen, dead world. Instead, Triton showed that tidal heating, internal chemistry, and perhaps a subsurface ocean could sustain activity even in the outer solar system. Voyager 2's flyby transformed Triton from an afterthought into one of the most intriguing moons in the entire solar system. On a symbolic level, the Neptune encounter marked the end of humanity's first great wave of planetary exploration. With Neptune visited, every major planet in the solar system had been observed up close for the first time. From Mercury to Neptune, the Voyagers had stitched together a family portrait of the solar system, revealing its diversity and complexity. What had? Once been dots of light were now worlds with weather, mountains, oceans of gas, and surfaces carved by time and geology. The idea of the solar system as a static clockwork of planets gave way to the vision of a dynamic neighborhood, full of ongoing processes and mysteries. Neptune also reminded the world of the limits of a flyby mission. Voyager 2's closest approach lasted only hours, and in that short span it collected enough data to fill decades of study. Yet the fleeting nature of the encounter left vast gaps. We know little about Neptune's interior, its deeper weather patterns, or the long-term evolution of its rings and storms. We know Triton is active, but not how deep its activity runs, or whether it might harbor liquid water beneath its crust. The flyby whetted the appetite of planetary scientists, but it also left them with the frustration of unfinished business. In reflecting on Neptune, Voyager 2's triumph was not only scientific, but emotional. It was a reminder of what humanity could accomplish with imagination, engineering, and persistence. A spacecraft launched in 1977 had, more than a decade later, carried us to the edge of the solar system and revealed a planet no one had ever truly seen before. It gave Neptune a face, a personality, and a place in our collective imagination. When Voyager 2 left Neptune behind, it was as though the solar system's main story arc had reached its conclusion, and the spacecraft was now stepping into an epilogue, one that would take it into the stars themselves. When Voyager 2 left Neptune behind in August 1989, it marked the official end of the planetary Grand Tour. From Mercury to Neptune, every major planet had been visited up close for the first time in history. The missions had already surpassed their wildest expectations. But the story wasn't over. Both Voyager spacecraft were still functioning, their instruments still working, and their trajectories pointed them into the vast unknown beyond the solar system. It was at this point that the Voyager interstellar mission was born. This transition was less about a sharp change in operations and more about a shift in purpose. Instead of focusing on planetary encounters, Voyager 1 and Voyager 2 would now devote themselves to studying the outer reaches of the sun's influence, a region known as the heliosphere. The heliosphere is a vast bubble carved out of interstellar space by the solar wind, a stream of charged particles flowing outward from the sun at supersonic speeds. Understanding where the sun's influence ends and interstellar space begins had long been a goal of space science, but until the Voyagers, there had been no way to measure it directly. In the 1990s, both spacecraft continued to send back invaluable data. Their instruments measured cosmic rays, magnetic fields, and charged particles at distances where no spacecraft had ever gone before. They revealed how the solar wind changes as it expands, weakening with distance, and how cosmic rays from outside the solar system seep into the heliosphere. These observations provided the first direct evidence of the boundary regions at the edge of the sun's domain. This new mission also demonstrated the incredible resilience of the spacecraft. By the time they left Neptune, each Voyager was more than a decade old, far past its original design lifetime. Their power came from radioisotope thermoelectric generators, RTGs, which convert the heat from decaying plutonium into electricity. Though the output slowly decreased each year, it was enough to keep the spacecraft alive. Engineers at NASA devised clever strategies to conserve power, turning off non-essential instruments and systems while prioritizing those best suited for interstellar science. The shift in mission also changed the way scientists and the public thought about the Voyagers. They were no longer just planetary explorers, but ambassadors of Earth, carrying their golden records into the galaxy. They became testaments to human curiosity and endurance, pressing outward into a region where no human-made object had ever ventured. This stage of their mission bridged the familiar solar system with the unknown expanse of the Milky Way. As the 1990s gave way to the 2000s, the question became not whether the Voyagers would keep working, but how far they could go. No one knew exactly where the edge of the heliosphere lay, or how long the spacecraft's instruments would last. Each new year of data brought both anticipation and anxiety. Anticipation of what they might discover, and anxiety that one day the faint signals from these distant travelers would fall silent. Yet against all odds, the Voyagers kept going, proving themselves not just as explorers of planets, but as pioneers of interstellar space. As Voyager 1 and Voyager 2 pressed outward in the years following their planetary encounters, they entered a realm that had only existed in theory. The Sun's influence extends far beyond the orbit of Pluto, creating a protective bubble called the heliosphere. This bubble is formed by the solar wind, a continuous flow of charged particles streaming outward from the Sun, and it serves as a shield against cosmic rays and interstellar material. Understanding the shape, size, and dynamics of the heliosphere had been one of the long-standing questions of space physics, and the Voyagers were uniquely positioned to provide the first direct answers. The outer structure of the heliosphere was thought to consist of several layers. Closest to the Sun is the supersonic solar wind, which gradually slows as it collides with the thin gas of interstellar space. At a certain point, the solar wind slows to subsonic speeds, creating a boundary known as the termination shock. Beyond that lies the heliosheath, a turbulent zone where the slowed solar wind mingles with interstellar material. The final boundary, called the heliopause, marks the point where the Sun's influence ends and interstellar space truly begins. Voyager 1 and Voyager 2 became our probes into these unknown regions. As they traveled farther, their plasma instruments, magnetometers, and cosmic ray detectors recorded subtle changes in the environment. By the early 2000s, Voyager 1 began detecting evidence of the termination shock. In 2004, it officially crossed this boundary, providing the first in situ confirmation of its existence. Voyager 2 followed in 2007, crossing at a different distance, which indicated that the heliosphere is not perfectly spherical, but instead distorted by the pressure of the interstellar medium. Within the heliosheath, the Voyagers discovered a region of surprising complexity. Instead of a smooth flow of particles, the spacecraft detected turbulence, shocks, and fluctuations in magnetic fields. Cosmic rays, normally deflected by the heliosphere, began to appear in greater numbers, leaking through the boundary as the spacecraft pressed outward. These observations revealed that the edge of the solar system is not a quiet frontier, but a dynamic and constantly shifting zone where the Sun and the galaxy interact. One of the most important discoveries was that the solar wind itself changes over time, influenced by the Sun's 11-year activity cycle. During periods of high solar activity, the heliosphere expands, pushing the boundaries outward. During quieter times, it contracts, allowing more interstellar particles to seep in. The Voyagers, by observing these changes firsthand, turned abstract models into measurable realities. The data gathered by the two spacecraft also had profound implications for Earth. By better understanding how the heliosphere deflects harmful cosmic rays, scientists could refine their models of how radiation in space might affect astronauts and spacecraft beyond Earth's protective magnetic field. The Voyagers, in other words, were not just answering abstract scientific questions, but were providing practical knowledge for the future of human space exploration. As the spacecraft moved closer to the heliopause, anticipation grew. What would it be like to cross into interstellar space? Would the transition be sudden or gradual? Would instruments survive long enough to record the moment? The heliopause represented not only a scientific milestone, but also a symbolic one, the line between our Sun's domain and the rest of the galaxy. The Voyagers were humanity's messengers, pressing ever closer to that historic crossing. On August 25, 2012, nearly 35 years after its launch, Voyager 1 achieved something no human-made object had ever done before. It crossed into interstellar space. For decades, scientists had speculated about where the boundary of the Sun's influence might lie, but Voyager 1 gave the first direct measurement. At a distance of about 121 astronomical units from the Sun, roughly 18 billion kilometers, 11 billion miles, the spacecraft finally pierced the heliopause, the invisible frontier where the solar wind yields to the pressure of the interstellar medium. The transition was not marked by fireworks or dramatic images, but by subtle and profound changes in the data. Instruments detected a sudden drop in the number of charged particles originating from the Sun, while the number of high-energy cosmic rays from outside the solar system spiked. The spacecraft's magnetometer also confirmed that the magnetic field around Voyager 1 was now aligned with the galactic environment rather than with the Sun's field. These combined indicators made it clear Voyager 1 had left the bubble of the heliosphere and was now sailing among the stars. This achievement was not just a triumph of engineering, but a historic moment in the story of humanity. For the first time, an artifact of human civilization had left the protective cocoon of our sun's reach and entered the space between stars. Voyager 1 became a symbol of exploration at its purest, venturing where no human eye had ever seen, where no telescope could directly probe, and where no spacecraft had dared to go. The crossing also provided unprecedented science. The density of plasma measured by Voyager 1 revealed that the interstellar medium was denser than models had predicted, reshaping theories about the environment surrounding our solar system. It showed that the heliosphere acts as a shield, absorbing and deflecting much of the cosmic radiation that constantly bombards interstellar space. Understanding this environment has direct implications for the safety of future human missions. Beyond the protective shield of Earth and the Sun, Voyager 1's entry into interstellar space was celebrated worldwide. NASA announced the milestone with a sense of awe, highlighting the spacecraft's distance. Signals from Voyager 1 now took over 17 hours to reach Earth, traveling at the speed of light. The faint whispers of data carried across unimaginable distances were reminders of both the vastness of the cosmos and the extraordinary persistence of human technology. Even more remarkable was the fact that Voyager 1 was still operational, despite being launched in 1977 with technology far less advanced than today's smartphones. Its instruments were designed for a mission of only 5 years, yet decades later, they continued to send back data that no other spacecraft could. The spacecraft became an enduring metaphor for resilience, patience, and the long arc of human ambition. While Voyager 1 is now in interstellar space, it is still not beyond the Sun's gravitational reach. It will remain bound to the solar system until it drifts close to another star, something that will not happen for tens of thousands of years. But symbolically, the crossing of the heliopause represented humanity's first true step into the galaxy. The spacecraft is now a silent traveler among the stars, carrying with it a message of who we are and what we value, inscribed on the golden record attached to its side. While Voyager 1 claimed the title of the first spacecraft to reach interstellar space, Voyager 2 followed with its own historic crossing 6 years later. On November 5, 2018, Voyager 2 passed beyond the heliopause at a distance of about 119 astronomical units from the Sun, slightly closer than Voyager 1 had done. This confirmed that the heliosphere is not a perfect bubble, but an irregular dynamic boundary shaped by both the solar wind and the surrounding interstellar medium. Unlike Voyager 1, Voyager 2 still had a working plasma science instrument at the time of its crossing, making its data especially valuable. This instrument directly measured the density and speed of charged particles in the solar wind as the spacecraft moved outward. As Voyager 2 approached the heliopause, the solar wind slowed dramatically, and the density of interstellar plasma rose sharply, a clear indicator of the transition from the Sun's domain into the broader galaxy. The drop in solar originating particles and the simultaneous rise in galactic cosmic rays mirrored what Voyager 1 had seen, confirming that both spacecraft had indeed entered interstellar space. Voyager 2's crossing not only corroborated Voyager 1's findings, but also added critical details. For example, it revealed that the pressure of the interstellar medium is stronger than expected, squeezing the heliosphere into a more asymmetrical shape. This explained why the two spacecraft crossed into interstellar space at different distances. Voyager 2's plasma data also provided a rare direct glimpse of the properties of the medium between stars, information that was otherwise unattainable without leaving the heliosphere. The milestone underscored how extraordinary the Voyager mission had become. More than 4 decades after launch, both spacecraft were still working, still sending back data, and still breaking records. Engineers at NASA continued to monitor their health, carefully rationing power as their plutonium-based generators steadily declined. Non-essential instruments had been switched off long ago, but the most critical sensors remained active, allowing the spacecraft to continue their unprecedented exploration of interstellar space. For humanity, the fact that 2 spacecraft had now crossed into the galaxy carried profound symbolic weight. It showed that Voyager 1's feat had not been a fluke, and that our technology was capable of surviving and operating in the most distant and hostile regions ever reached. Voyager 2's crossing also served as a reminder of the mission's endurance. A spacecraft built with 1970s technology had outlasted countless newer machines. Its longevity owed to meticulous design, careful planning, and decades of ingenuity by teams of scientists and engineers. With both Voyagers now beyond the heliopause, the mission entered a new chapter. No longer were they just planetary explorers or heliosphere probes. They had become emissaries of Earth, drifting into the galaxy while carrying their golden records, tiny capsules of humanity's voice, music, and culture. In the silence of interstellar space, they continued to broadcast their faint signals back to Earth, reminders of humanity's insatiable curiosity and its drive to see what lies beyond the horizon. When Voyager 1 and Voyager 2 slipped into interstellar space, they became our first direct probes of the environment between the stars. For centuries, astronomers had speculated about what existed beyond the sun's protective bubble. Theoretical models predicted a tenuous mix of charged particles, magnetic fields, and cosmic rays, but no one could be certain. With their hardy instruments still functioning, the Voyagers transformed speculation into direct observation. One of the most important measurements was of plasma density. The space between stars is not empty. It is filled with a thin soup of ionized gas. Voyager 1, though lacking a working plasma instrument, was able to detect plasma oscillations in 2013, caused by a solar storm ripple passing through the region. These oscillations revealed that the density of interstellar plasma was about 40 times greater than the plasma inside the heliosphere. Voyager 2's still active plasma instrument later confirmed this density directly, providing a clearer picture of the interstellar medium. Magnetic field measurements also proved invaluable. As the spacecraft moved beyond the heliopause, they detected that the orientation of the magnetic field shifted, aligning more closely with that of the galaxy rather than the sun. This confirmed that they had entered a new domain of space, one dominated not by the solar wind, but by the broader galactic environment. Yet curiously, the magnetic fields just outside the heliopause were stronger and more ordered than expected, suggesting that the boundary region is far more complex than scientists had imagined. The Voyagers also became detectors of cosmic rays, high-energy particles that originate from distant supernovae and other energetic astrophysical phenomena. Inside the heliosphere, many of these cosmic rays are deflected or weakened by the solar wind. Outside the heliopause, the spacecraft recorded a dramatic increase in their intensity. By measuring the energy and frequency of these cosmic rays, the Voyagers helped scientists refine models of how the heliosphere shields the planets, including Earth, from some of the harshest radiation in the galaxy. Beyond the hard numbers, the science of interstellar space carried profound implications for humanity's future. If humans are ever to travel beyond the heliosphere, they will have to contend with a radiation environment much harsher than what is found within the Sun's protective bubble. The data provided by the Voyagers offers the first real-world guide to what such journeys would entail. It also informs the design of future spacecraft, which will need stronger shielding and more robust systems to survive the bombardment of galactic cosmic rays. Voyager 1 and Voyager 2 also demonstrated the remarkable reach of human communication. Even at distances exceeding 20 billion kilometers, over 12 billion miles, their faint radio signals are still detected by NASA's Deep Space Network, which listens with enormous radio antennas spread across Earth. The fact that instruments built in the 1970s can still transmit usable data across such immense distances is a triumph of engineering, one that highlights the foresight of the mission's original designers. In many ways, the science of interstellar space provided by the Voyagers is both humbling and tantalizing. These spacecraft are only just outside the Sun's protective bubble, still in a region called the local interstellar cloud. To reach true interstellar emptiness, they would need to travel much farther, a journey that will take tens of thousands of years. Yet even in this first step, the Voyagers have given humanity a taste of what lies beyond. For the first time, we are not just imagining the interstellar medium, we are measuring it. One of the greatest marvels of the Voyager mission is not just that the spacecraft are still operating decades after launch, but that we can still talk to them at all. At more than 20 billion kilometers away, the signals from Voyager 1 and Voyager 2 take over 18 hours to travel one way to Earth. By comparison, a message from the Moon takes about 1.3 seconds. Communicating with the Voyagers is less like a phone call and more like sending a postcard into the abyss and waiting weeks for the reply. The signals themselves are unimaginably faint. By the time a Voyager's transmission reaches Earth, its power has diminished to less than a billionth of a watt, a whisper among cosmic noise. Detecting it requires the massive antennas of NASA's Deep Space Network, DSN, located in California, Spain, and Australia. These dishes, some up to 70 meters wide, are among the most sensitive radio receivers ever built. Without them, the faint voice of the Voyagers would be lost to the background hum of the universe. Even with this infrastructure, communicating with the spacecraft requires careful scheduling and incredible patience. Commands must be compact, efficient, and free of error, because resending corrections can take more than a day. Engineers also have to contend with the limited data rate. At interstellar distances, Voyager 1 transmits at just 160 bits per second, slower than the dial-up modems of the early internet. Yet even at this snail's pace, the spacecraft have delivered groundbreaking data about the edge of the heliosphere and the interstellar medium beyond. The distance also creates unique challenges in troubleshooting. When Voyager 2 suffered a memory glitch in 2020 that caused its instruments to shut down, engineers had to carefully construct and send commands without immediate feedback, waiting more than 34 hours for a full round-trip confirmation. The fact that this process succeeded is a testament not only to NASA's engineering ingenuity, but also to the persistence and creativity of the mission team. As the spacecraft move ever farther from Earth, the challenge grows. The signals will eventually become too weak to detect, and the DSN may one day be unable to keep up with the increasing time delays and fading transmissions. But for now, against all odds, the Voyagers remain connected, continuing to whisper their discoveries across the gulf of space. The story of Voyager is more than just a tale of machines exploring the outer planets. It is a story about human ambition, resilience, and the drive to reach beyond what seems possible. When the spacecraft launched in 1977, no one realistically expected them to still be functioning more than 4 decades later. The missions were originally designed for 5 years, long enough to explore Jupiter and Saturn. Yet through careful management, brilliant improvisation, and no small measure of luck, Voyager 1 and Voyager 2 have gone on to rewrite textbooks, inspire generations, and expand humanity's footprint into interstellar space. The scientific legacy is immense. Voyager gave us our first close-up views of Jupiter's Great Red Spot and volcanic Io, Saturn's complex rings, Uranus's tilted magnetosphere, and Neptune's supersonic winds. It confirmed theories, shattered assumptions, and introduced mysteries that continue to puzzle astronomers. Beyond planetary science, the probes provided humanity's first direct measurements of the boundary of the heliosphere and the environment of the interstellar medium. These data are unique, as no other spacecraft has yet ventured so far. Culturally, the Voyagers are immortalized through the Golden Record, a time capsule of sounds, images, and messages meant for any extraterrestrial intelligence that might one day encounter them. This record turns the spacecraft into more than scientific instruments. They are ambassadors of Earth, carrying the essence of our species out into the cosmos. Whether or not the record is ever found, its existence speaks volumes about our curiosity and desire for connection. The future of the probes is both certain and bittersweet. Power supplies are dwindling, and NASA engineers are gradually shutting down instruments to extend the missions as long as possible. By the late 2020s or early 2030s, the spacecraft will likely fall silent, their nuclear batteries no longer able to generate enough electricity. At that point, they will drift endlessly, silent wanderers in the interstellar sea. They will continue to orbit the center of the Milky Way for billions of years, long after Earth itself may no longer exist. In this way, Voyager's legacy is eternal. It has already reshaped our understanding of the solar system and reminded us of our small but determined place within the universe. For the scientists who guided them, the engineers who problem-solved impossible glitches, and the millions who followed their journeys from Earth, the Voyagers embody the best of human curiosity and perseverance. They prove that even fragile machines, launched by a small blue planet, can touch the stars, and that humanity's reach, like its imagination, is boundless. The Voyager mission is often remembered for its images of the giant planets and its role in pushing humanity into interstellar space. But its true legacy also lies in the countless lessons it taught us about science, engineering, and our place in the cosmos. Those lessons shape not only the way we design spacecraft, but also how we think about exploration itself. In many ways, Voyager was not just a mission, it was a teacher, leaving behind insights that continue to guide us nearly half a century later. One of the most important lessons from Voyager was the value of engineering for longevity. When the spacecraft launched in 1977, its planned mission was supposed to last only 5 years, long enough to fly by Jupiter and Saturn. Yet the engineers who built it decided to include redundancies, backup systems, and flexibility far beyond the minimum requirements. For example, Voyager carried multiple gyroscopes and thrusters to control orientation, redundant computers for essential commands, and carefully shielded instruments designed to withstand the radiation environments of Jupiter. No one truly expected the spacecraft to last more than a decade, but the decision to design conservatively meant that Voyager was able to endure far longer than anyone dared to predict. Today, more than 4 decades later, those choices are the reason it is still transmitting data from interstellar space. Another lesson was that spacecraft must be able to adapt long after launch. Voyager's computers are primitive by modern standards, holding only about 68 kilobytes of memory, less than what is needed to store a single modern digital photo. Yet the spacecraft have been reprogrammed dozens of times during their journey. Engineers had to invent entirely new sequences of commands to operate instruments in ways never envisioned in the 1970s. When one instrument began to degrade, the team often found creative workarounds, like rerouting commands or changing the power supply schedule. One particularly dramatic example involved managing the hydrazine fuel used for attitude control. As Voyager aged, engineers realized the tiny thrusters responsible for keeping the antenna pointed at Earth were beginning to wear out. In a remarkable feat, They reactivated backup thrusters that had not been used in decades, extending the mission by years. These feats showed that resilience and ingenuity are just as important as initial design. Voyager also provided lessons about the value of remote teamwork and international cooperation. Over the decades, thousands of people contributed to keeping the mission alive, many of whom were not even born when the spacecraft launched. Knowledge had to be passed down from one generation of scientists and engineers to the next, ensuring that critical expertise was never lost. This intergenerational continuity became a model for long-duration missions, showing that exploration is not the work of a single moment or team, but of an entire lineage of human effort. The Deep Space Network, with its massive antennas in California, Spain, and Australia, also highlighted the necessity of global infrastructure for space exploration. Without constant communication across hemispheres, Voyager would have vanished from our reach decades ago. From a scientific standpoint, Voyager delivered another essential lesson: always expect the unexpected. Prior to the flybys, many scientists predicted that the outer planets and their moons would be quiet, frozen, and geologically dead. Instead, Voyager revealed one astonishing surprise after another. At Io, Voyager discovered active volcanoes, the first seen anywhere beyond Earth, proving that tidal forces could generate enough heat to keep a moon volcanically alive. Europa showed signs of a possible subsurface ocean beneath its icy crust, sparking decades of speculation about extraterrestrial habitats. Saturn's moons revealed intricate features, including the braided structure of its rings and mysterious surface markings on Enceladus. Uranus surprised scientists with its tilted magnetic field and its bizarre moon Miranda, scarred with giant cliffs and ridges, unlike anything in the solar system. Neptune revealed supersonic winds and geysers erupting from the surface of Triton. Time and again, Voyager forced us to abandon assumptions and reminded us that nature is far more inventive than human imagination. This lesson carried over to later missions. The Galileo spacecraft, which orbited Jupiter in the 1990s, was specifically equipped to study Europa's ocean in more detail because Voyager had shown its promise. Cassini, sent to Saturn, was designed with instruments that could probe Enceladus and Titan in ways Voyager could not. Even the New Horizons mission to Pluto was shaped by Voyager's example, preparing scientists to expect landscapes stranger than predictions. In each case, Voyager proved that the best discoveries come not from confirming what we expect, but from revealing what we never dreamed of. Voyager also taught us about the importance of perspective. The famous pale blue dot image, captured in 1990 as Voyager 1 looked back toward Earth from billions of kilometers away, carried a lesson that was not scientific in the traditional sense, but philosophical. It reminded humanity that everything we know, every war, every triumph, every life, takes place on a single tiny world suspended in the vastness of space. Carl Sagan, who helped inspire the photograph, used it to teach us humility and unity, emphasizing that our divisions and conflicts are trivial compared to the scale of the universe. This philosophical lesson is perhaps as valuable as any scientific discovery. It continues to shape public support for exploration by showing that missions like Voyager are not just technical endeavors, but mirrors reflecting our place in the cosmos. Finally, Voyager taught us about endurance, not just mechanical endurance, but human persistence. The mission required constant problem solving, relentless patience, and faith that discoveries would come. Even when Voyager moved beyond the planets, many argued that it no longer had value, but the team pressed on, gathering data about cosmic rays, the solar wind, and the interstellar medium. In 2012, when Voyager 1 officially crossed into interstellar space, it became clear that the patience had paid off. Humanity had left the solar bubble and touched the galaxy directly. That milestone was possible only because of decades of endurance, both from the spacecraft and the people who refused to give up on it. In the end, the greatest lesson of Voyager is that exploration is not about reaching a destination, but about embracing the journey. The spacecraft may one day fall silent, but the wisdom it gave us will endure. Teaching engineers how to build for the long haul, teaching scientists to expect the unexpected, and teaching humanity to look at itself from a broader perspective. Voyager showed that even with limited tools and technology, the human spirit of exploration can carry us further than we ever imagined. When Voyager was launched in 1977, the question of life beyond Earth was a matter of speculation and imagination. The scientific community had only recently begun to appreciate how extreme environments on Earth, such as hydrothermal vents at the bottom of the ocean, could sustain vibrant ecosystems. Space exploration was still young, and most believed that the outer solar system would be a frozen, lifeless expanse. Voyager changed that perception forever. Although the twin spacecraft did not carry the instruments needed to detect biology directly, the clues they uncovered reshaped the search for habitable environments in our solar system and beyond. One of the most striking revelations came from Jupiter's moon Io. Before Voyager, scientists expected Io to be a cratered, frozen body like Earth's moon. Instead, the spacecraft revealed a world literally alive with volcanoes, the first active ones discovered beyond Earth. Massive eruptions were seen blasting sulfur and lava into space, reshaping the surface before Voyager's cameras. The discovery proved that tidal forces, the gravitational tug-of-war between Jupiter and its other moons, could keep a small world volcanically active. This was not just a geological surprise. It showed that moons could have internal heat sources independent of their distance from the sun. For astrobiology, it opened the door to a profound idea. Environments capable of sustaining energy, chemistry, and change, the basic ingredients for life, could exist far from the traditional habitable zone. Even more compelling was Europa, another of Jupiter's moons. Voyager's cameras showed its surface crisscrossed with cracks and ridges, with few impact craters. That suggested the surface was geologically young and constantly resurfaced. Scientists began to suspect that beneath its icy shell lay a hidden ocean of liquid water, kept warm by tidal heating. This idea was revolutionary. Until then, liquid water was assumed to exist only on planets within the right temperature range from the sun. Voyager showed that water could exist in abundance even in the frozen reaches of the solar system. While Voyager could not confirm the ocean, the evidence it provided laid the foundation for decades of research that followed. Today, Europa is one of the prime targets in the search for extraterrestrial life, with NASA's Europa Clipper mission scheduled to explore it in the coming years. That mission would not exist without Voyager's initial discoveries. Saturn provided more revelations. Titan, the largest of Saturn's moons, was shown by Voyager to have a thick, hazy atmosphere, denser than Earth's. Scientists were astonished to learn that. Titan's atmosphere was made largely of nitrogen, with traces of methane and complex organic molecules. These chemicals are considered building blocks for life. Titan's surface could not be clearly seen by Voyager because of the dense haze. But the very fact that such an atmosphere existed suggested processes that might echo the chemistry of early Earth. In the decades since, Titan has become one of the most intriguing objects in the solar system, leading to missions like Cassini-Huygens, which later confirmed the presence of lakes and rivers of liquid methane and ethane on the surface. Even now, NASA is preparing the Dragonfly mission, a nuclear-powered drone designed to fly across Titan's alien landscape in search of clues about prebiotic chemistry. Voyager's first glimpse of Titan made all of this possible. Voyager also hinted at mysteries surrounding other Saturnian moons, such as Enceladus. Though Voyager did not directly observe the geysers later discovered by Cassini, its images suggested unusual surface features and hinted at internal activity. These subtle clues were enough to encourage scientists to keep an eye on Enceladus, which would later prove to host subsurface oceans with active plumes venting water vapor and organic compounds into space. In hindsight, Voyager planted the seeds of our modern fascination with this icy moon as a potential haven for microbial life. When Voyager 2 moved on to Uranus and Neptune, the surprises continued. At Uranus, the moon Miranda displayed a surface unlike any seen before: giant cliffs, fractured canyons, and regions that looked patchworked together as though the moon had been shattered and reassembled. While Voyager could not confirm the presence of subsurface oceans at Uranus's moons, the bizarre geology suggested past internal activity. At Neptune, Triton astonished scientists by showing active geysers erupting nitrogen into the thin atmosphere. Triton was no frozen relic, it was alive with energy. Given that Triton is likely a captured Kuiper Belt object, this discovery suggested that other icy worlds at the edge of the solar system could also be geologically active and possibly habitable. In all these cases, Voyager revealed that life's potential habitats might not be limited to planets orbiting at the right distance from a star. Instead, it showed that moons could provide equally compelling environments, heated not by sunlight but by the flexing and stretching of gravitational forces. This shifted the very framework of astrobiology. Suddenly, the idea that life might exist in hidden oceans beneath ice shells became a serious scientific possibility, one that continues to drive missions today. Beyond the solar system, Voyager's contributions also extended to exoplanet science. By studying the atmospheres of the giant planets, Voyager provided essential data on cloud dynamics, chemical compositions, and weather systems that now serve as models for interpreting exoplanetary observations. When astronomers use telescopes to analyze the light passing through the atmosphere of a distant gas giant orbiting another star, they rely on the foundational knowledge gained from Voyager's studies of Jupiter, Saturn, Uranus, and Neptune. The mission gave scientists a reference library of planetary atmospheres that could be applied far beyond our own system. Voyager's influence on the search for life is also cultural. The Golden Record carried aboard both spacecraft symbolized humanity's desire not only to explore, but also to connect. It contained greetings in dozens of languages, music from around the world, and sounds of nature. A declaration that life on Earth exists and seeks companionship in the cosmos. While the record is not a scientific instrument, it represented a philosophical commitment to the search for life, encapsulating the idea that exploration is not just about discovery, but also about communication. The ongoing fascination with Voyager's discoveries has directly shaped funding and priorities for later missions. Without Voyager, we might not have prioritized Europa, Enceladus, and Titan as central to astrobiology. Without Voyager, we might still assume that life could only exist on Earth-like planets. Instead, the mission expanded our imagination and gave us a new map of possible habitats, both near and far. In many ways, Voyager taught us that the universe is more generous than we thought. Life might not be confined to one fragile planet, orbiting at just the right distance from its star. It could hide beneath ice, thrive in oceans sealed away from sunlight, or emerge in chemical soups beneath alien skies. While Voyager never detected life, it pointed us toward the places we must look. And in doing so, it brought us closer than ever to answering the most profound question: are we alone? When we talk about Voyager, it is impossible not to compare it with the missions that came before and after. In some ways, Voyager represents the culmination of early space exploration, the logical extension of missions like Pioneer 10 and 11. In other ways, it is the ancestor of modern planetary missions, a giant whose shoulders later spacecraft stood upon. Comparing Voyager to other missions helps us understand not only its achievements, but also why it still occupies such a singular place in history. The most natural comparison is with the Pioneer program. Pioneer 10, launched in 1972, was the first spacecraft to cross the asteroid belt and make a direct flyby of Jupiter. Pioneer 11, launched in 1973, went on to fly by both Jupiter and Saturn. These missions were pathfinders in every sense of the word, testing navigation techniques, spacecraft durability, and the ability to gather data in the harsh outer solar system. Without Pioneer, Voyager could never have succeeded, yet Pioneer was limited in both instrumentation and ambition. Its cameras provided only rough images, its instruments were fewer in number, and its mission lifetime was not expected to stretch decades. Voyager built upon this foundation by carrying more advanced instruments, using more powerful communication systems, and daring to aim not just for Jupiter and Saturn, but for the entire outer solar system. Where Pioneer opened the door, Voyager strode confidently through it. Cassini is another mission frequently compared with Voyager, particularly because both explored Saturn. Launched in 1997 and arriving at Saturn in 2004, Cassini orbited the planet for 13 years, offering a level of detail Voyager could never match in a flyby. Cassini revealed Enceladus's geysers in extraordinary detail, mapped Titan's lakes of liquid methane, and observed Saturn's rings in ways that transformed our understanding. Yet it is important to remember that Voyager paved the way. Without Voyager's first look at Titan's atmosphere, Enceladus's strange surface, or the complex structure of Saturn's rings, Cassini might not have been designed the way it was. Voyager showed us where the mysteries were. Cassini followed up with the tools to investigate them thoroughly. In this sense, Voyager and Cassini are partners across time, one the scout, the other the settler. New Horizons, launched in 2006 and reaching Pluto in 2015, has often been described as Voyager's spiritual successor. Like Voyager, it was a flyby mission, racing past its target at incredible speed and capturing the first close-up images of a distant world. Just as Voyager revealed Uranus and Neptune for the first time, New Horizons transformed Pluto from a fuzzy dot into a vibrant world with mountains, glaciers, and a dynamic atmosphere. The two missions share a similar spirit of exploration, the willingness to go further, to see what no one has seen before. But while New Horizons visited a single dwarf planet before moving on into the Kuiper Belt, Voyager visited 4 giant planets and dozens of moons, a feat unmatched in the history of space exploration. New Horizons will drift into interstellar space, just as Voyager has, but it will never match the sheer variety of discoveries that Voyager made. The Hubble Space Telescope also invites comparison, though its mission was quite different. Launched in 1990, Hubble has peered deep into the universe, capturing galaxies billions of light years away. While Voyager explored by traveling outward, Hubble explores by looking outward. Both missions revolutionized our understanding of the cosmos, but in different ways. Voyager gave us the first close-up views of planets in our own solar system, while Hubble revealed the scale and beauty of the universe beyond. Together, they symbolize 2 approaches to exploration, the traveler and the observer. One carries human engineering into the unknown. The other brings the unknown to us through light. The James Webb Space Telescope, launched in 2021, can also be seen as part of this lineage. Like Hubble, it observes rather than travels, but its ability to analyze exoplanet atmospheres connects directly to Voyager's legacy. Voyager's study of planetary atmospheres within our solar system gave scientists the baseline they needed to interpret the strange worlds Webb now studies. In this way, Webb's deep space science is linked directly to Voyager's planetary science. One looks at distant stars, the other looked at nearby giants. Both expand the boundaries of what humanity can know. Voyager also stands apart from robotic landers and rovers. Missions like the Viking landers on Mars in the 1970s, the Spirit and Opportunity rovers in the 2000s, and the Perseverance rover today all represent different kinds of exploration. They dig into the soil, analyze rocks, and search for signs of habitability. Voyager never touched down, but instead gave us the grand tour, a survey of the solar system at its largest scale. Landers and rovers give us intimacy. Voyager gave us perspective. Both are essential, but Voyager's role was unique in stitching together the larger story of planetary diversity. Even future missions can be compared to Voyager. NASA has proposed an interstellar probe, a spacecraft that would launch in the coming decades with the specific goal of studying the outer heliosphere and beyond. Breakthrough Starshot imagines sending tiny probes propelled by lasers to another star system. These concepts are often described as the next Voyagers, following in the trail first blazed in 1977. Whether or not they succeed, the fact that Voyager is the benchmark shows how enduring its legacy is. One reason Voyager continues to stand out in these comparisons is its dual nature. It was both a planetary mission and an interstellar mission. Most spacecraft are one or the other. Cassini orbited Saturn but never left. New Horizons will leave the solar system but studied only one primary target. Voyager did both. It revealed the outer planets in detail while also carrying humanity's first emissary into interstellar space. That combination is why it remains unmatched. Voyager is also unique because of the golden record. While no other spacecraft has carried such a deliberate cultural message, Voyager's inclusion of the record set a precedent for thinking of missions as not just scientific, but also symbolic. It was not enough to gather data. Voyager also carried our story. Later missions have followed this tradition in smaller ways, plaques, signatures, or symbolic items, but none with the grandeur of Voyager's message to the stars. In this way, Voyager blurred the line between science, culture, and philosophy, something no other mission has done to the same extent. When all these comparisons are made, what emerges is not just a sense of Voyager's accomplishments, but also its uniqueness. Other missions may have gone deeper into individual worlds, observed with higher resolution, or looked farther into the cosmos, but none have matched Voyager's combination of breadth, endurance, and cultural impact. Voyager was not just another mission, it was a turning point. It set the standard for exploration and continues to define what it means to leave home and venture into the unknown. When Voyager launched in 1977, few people believed humanity would ever build another spacecraft to go further. At the time, the idea of sending machines beyond the solar system felt more like science fiction than science. Yet here we are more than 4 decades later, with both Voyagers still operating at the very edge of interstellar space, and with scientists and engineers actively sketching plans for what might come next. The future of deep space exploration is no longer a distant dream. It is a roadmap slowly taking shape, and Voyager has provided the template. The first element of this roadmap involves continuing the work that Voyager began, studying the heliosphere and the transition into interstellar space. Voyager 1 and 2 have provided the first direct measurements of this boundary region, showing how the solar wind, the stream of charged particles flowing from the sun, interacts with the surrounding interstellar medium, yet their instruments were not designed with this mission in mind. They are limited in sensitivity, and many of their systems have already been turned off to conserve power. For this reason, NASA and other agencies have proposed building a dedicated interstellar probe. This spacecraft would be designed from the start to study the edge of the heliosphere and beyond, carrying instruments capable of measuring cosmic rays, magnetic fields, plasma flows, and dust in unprecedented detail. One of the most ambitious proposals suggests launching such a probe by the 2030s, using a powerful rocket like the Space Launch System or a future heavy-lift vehicle. With modern propulsion and trajectory planning, the spacecraft could reach distances of 1,000 astronomical units, more than 20 times further than Voyager, within a human lifetime. Such a mission would provide a true global view of the solar system's boundary, something Voyager could only hint at. Engineers are already grappling with questions of power, communication, and durability using Voyager's lessons as a guide. Another frontier lies in propulsion itself. Voyager relied on gravity assists from the giant planets to achieve its high speeds. This method, though elegant, required rare planetary alignments and limited the directions in which spacecraft could travel. Future missions may break free of these constraints by developing advanced propulsion technologies. Nuclear electric propulsion, for example, could allow spacecraft to accelerate gradually but continuously over decades, reaching much higher speeds than Voyager. Solar sails, propelled by the pressure of sunlight or even by powerful Earth-based lasers, offer another possibility. Concepts like breakthrough starshot imagine tiny probes the size of postage stamps accelerated to a significant fraction of the speed of light by laser arrays, potentially reaching the Alpha Centauri system in just a few decades. These ideas are still experimental, but they represent the bold ambition of a new generation inspired by Voyager's achievements. Beyond propulsion, the question of how spacecraft can endure decades or centuries in deep space looms large. Voyager taught us that redundancy, simplicity, and careful power management are essential, but future interstellar probes may need to last far longer. Scientists are already discussing the possibility of using artificial intelligence to help spacecraft operate autonomously when communication delays stretch into days or weeks. Self-repairing systems, modular components, and new power sources such as advanced radioisotope generators or even miniature nuclear reactors could become essential. In this sense, the future of deep space exploration may depend as much on breakthroughs in computing and materials science as on rockets and propulsion. The scientific goals of future missions will also reflect Voyager's legacy. We now know that some of the most intriguing environments for life exist on icy moons, such as Europa, Enceladus, and Titan. Missions are already being prepared to study these worlds in greater detail. The Europa Clipper will launch later this decade to orbit Jupiter and investigate the moon's icy crust and hidden ocean. Dragonfly, a drone-like craft, will fly across Titan's surface in the 2030s, searching for prebiotic chemistry in its methane lakes and dunes. These missions are, in many ways, the grandchildren of Voyager, carrying forward the first tantalizing clues it provided. Looking even further, the idea of exploring exoplanets, worlds orbiting distant stars, looms on the horizon. While interstellar probes capable of reaching other star systems remain theoretical, telescopes like the James Webb Space Telescope and its successors are already peering into the atmospheres of exoplanets, searching for water vapor, methane, and other signs of habitability. One can imagine a future in which interstellar probes, launched perhaps centuries from now, will follow in Voyager's footsteps and provide the first close-up views of alien worlds. When that day comes, Voyager will be remembered as the mission that first dared to step onto that path. The future of deep space exploration also raises profound questions about humanity's role in the universe. Voyager's golden record was a symbolic message to any beings that might one day encounter the spacecraft. Future missions may carry similar messages, perhaps more sophisticated ones that include digital archives of human knowledge, art, and culture. If we are to send emissaries into the galaxy, what should they say about us? Should they include only science, or should they also reflect our emotions, our creativity, and our flaws? These are not just technical questions, but philosophical ones. Questions Voyager forced us to consider for the first time. Another critical question is who will lead the next phase of exploration. In Voyager's era, space exploration was dominated by government agencies like NASA. Today, private companies such as SpaceX, Blue Origin, and others are playing increasingly central roles. It is conceivable that the first true interstellar probe could be built not by a national agency, but by a public-private partnership, or even by an international coalition. Voyager's global impact, inspiring people from every culture, suggests that future missions may benefit from being international endeavors from the outset. The scale, cost, and ambition of interstellar exploration may demand nothing less. There are also practical considerations. How do we ensure that spacecraft survive the hazards of interstellar space, such as micrometeoroids, cosmic radiation, and the sheer passage of time? Voyager showed that simple, rugged engineering could endure decades, but future missions may need to survive for centuries. Protective shielding, durable materials, and perhaps even hibernation modes will be needed. In many ways, we are only beginning to learn what it takes to build machines that can outlast civilizations. At the same time, the exploration of deep space is not just about technology, it is also about imagination. Voyager was launched during a period of cultural optimism about the future, a time when humanity dared to think on cosmic scales. If we are to continue, we must rekindle that sense of vision. The challenges are immense, but the rewards, new worlds, new knowledge, and new perspectives are equally vast. Voyager showed us that exploration is not a luxury, but a defining part of what it means to be human. Ultimately, the future of deep space exploration is already unfolding. From proposals for interstellar probes to missions aimed at Europa, Titan, and beyond, humanity is continuing the journey that Voyager began. The path ahead may be long, and it may take generations to realize the dream of reaching another star. But the seeds have already been planted, and when future spacecraft leave our solar system, carrying with them the knowledge and spirit of our species, they will do so in Voyager's shadow, following the trail blazed by two small probes launched in 1977 that refused to stop exploring. When the Voyager probes were launched in 1977, they were not built to last more than a few years. Their mission was to visit the outer planets, to give us a first glimpse of Jupiter, Saturn, Uranus, and Neptune. They were expected to serve as scouts, short-lived explorers that would quickly fade into the cold silence of deep space once their main objectives were completed. Yet here we are, nearly half a century later, still listening to the faint whispers of two spacecraft, more than 20 billion kilometers away. Their survival is itself a miracle of engineering and luck, but their meaning goes far deeper. Voyager is, at its heart, a human story. It is about our insatiable curiosity, our willingness to build fragile machines and throw them into the abyss simply to see what lies beyond. The data they sent back transformed our understanding of the solar system. We saw volcanic worlds like Io, icy landscapes like Europa, and storm systems that dwarfed the Earth. We realized that the giant planets were not static spheres of gas, but dynamic, living systems with moons that could harbor the conditions for life. Every image Voyager returned expanded our mental map of the cosmos and rewrote the textbooks. But Voyager's story is not only about science, it is also about time. These spacecraft have outlived the people who built them, the political climate that launched them, and even some of the technologies that powered their construction. They continue to operate in a world radically different from the one in which they were created. When Voyager was launched, personal computers were rare, and the internet was unimaginable. Today, we live in a networked digital world, and yet we are still communicating with 1970s technology drifting in the interstellar dark. This continuity reminds us that human achievement can transcend eras, that knowledge and perseverance have a way of carrying forward even as societies change. The golden records attached to each Voyager embody this continuity even more powerfully. They are not instruments for science, they are artifacts of hope. Carved onto their golden surfaces are the sounds of Earth, the music of humanity, greetings in dozens of languages, and images of who we are. They were intended for no one in particular, perhaps for aliens, perhaps for no one at all. In truth, they were a message to ourselves. They forced us to step outside our daily struggles and imagine what it means to be human from a cosmic perspective. For the first time, we packaged our identity as a species into a single artifact and sent it into the void. Whether or not anyone ever finds it, the act of sending it mattered. Voyager also changed how we view ourselves in relation to the universe. Carl Sagan, who helped design the Golden Record, later convinced NASA to turn Voyager 1's camera back toward Earth in 1990 from a distance of more than 6 billion kilometers. The resulting image, the pale blue dot, showed our planet as a tiny speck suspended in a sunbeam. That image has since become one of the most famous photographs ever taken. It reminds us that everything we love, everything we fight over, every joy and sorrow in human history has taken place on that small pixel. Voyager gave us that perspective, and it continues to humble us. As we look to the future, the Voyagers represent both inspiration and challenge. They have taught us what is possible when human beings dream boldly and commit to long-term exploration. They have also shown us the fragility of our presence in the cosmos. The spacecraft are slowing down, their power is dwindling, and eventually their voices will fall silent. Perhaps in a few years, perhaps in a decade, the last signal will fade, and Voyager will become a mute wanderer. But even then, their journey will not be over. They will continue to drift through the galaxy, carrying with them the Golden Record, a time capsule of humanity waiting to be discovered. There is a poetic symmetry in this. Voyager began as a scientific mission, but it has become a cultural one. Its legacy is not only in the data it transmitted, but also in the way it has captured our imagination. When people speak of Voyager, they rarely talk about magnetic field readings or plasma waves. They talk about the Golden Record, about the pale blue tau dot, about the audacity of sending 2 machines into interstellar space. These are not just scientific achievements, they are symbols of what it means to reach beyond ourselves. The story of Voyager also echoes a timeless truth. Exploration is not about immediate reward. The spacecraft cost money, time, and effort, and the benefits are not easily measured in profit or power. But exploration enriches humanity in other ways. It gives us knowledge, perspective, and a sense of unity. It reminds us that we are part of something larger, that our species is capable of acts of beauty and wonder. Voyager is, in a sense, a mirror. By gazing at the outer planets and the stars beyond, we are also gazing back at ourselves. As Voyager sails further into interstellar space, it leaves behind a trail for others to follow. Future missions, whether they are interstellar probes or telescopes capable of imaging Earth-like planets around distant suns, will be built on the foundation Voyager created. The idea that humans can send messages across billions of kilometers and still hear a reply was once unimaginable. Now it is proven. The idea that machines can last decades in deep space was once improbable. Now it is history. Voyager has expanded the possible, and the possible will only continue to grow. The final reflection must be this: Voyager is not just a spacecraft. It is us. It is our minds, our curiosity, our art, our voices, our laughter, our dreams. It carries a piece of humanity into the stars, a small but meaningful gesture of existence. Long after our civilizations have changed, long after our languages have shifted, long after even our descendants have forgotten the details of these times, Voyager will still be moving forward, carrying our story into the galactic ocean. In that sense, Voyager is immortal. To imagine the moment, millions or billions of years from now, when some other intelligence stumbles across this tiny probe, is to imagine humanity's most profound introduction. Perhaps they will play the Golden Record and hear Bach, or Chuck Berry, or greetings in Sumerian and Mandarin. Perhaps they will study the diagrams and realize that another species once lived near a small yellow star. Perhaps they will smile, recognizing in us the same spark of curiosity that drives them. Or perhaps they will never find it at all, and Voyager will drift forever as a lonely relic of a species that dared to dream. Either way, the message has already served its purpose. It has reminded us that we are part of a vast shared cosmos, and that our greatest legacy may be the courage to reach beyond ourselves. And so the story of Voyager is not ending, but continuing in every scientist who proposes an interstellar mission, in every child who looks at the stars with wonder, and in every person who understands that exploration is not about conquering space, but about finding our place in it. The spacecraft are still out there, still whispering to us, still carrying our voices into eternity. And long after the last signal fades, the memory of their journey will remain. For in the end, Voyager is not just about space. It is about humanity's endless voyage, the voyage of the mind and spirit, forever seeking the unknown. There is a certain quiet that comes when we think about Voyager's place in the universe. Two small spacecraft, no larger than a family car built with 1970s technology, are now the most distant objects humanity has ever made. They are beyond the planets, beyond the protective bubble of our sun's influence, sailing through the true interstellar medium. When we speak of them, we often forget how fragile they are. A single thin layer of insulation protects their instruments from the cold. A radioisotope generator, slowly fading with time, provides the last trickle of power. Their antennas are not giant beacons, but modest dishes, reaching across impossible distances. Yet somehow, those whispers cross the darkness and still find their way back to Earth. The story of Voyager is not only about exploration, but also about endurance. Endurance against time, against decay, against indifference. No one expected the spacecraft to still be alive this long, and yet they are. The engineers who launched them are retired or gone. The scientists who first analyzed their data are now legends. And still, these machines, carrying a small piece of Earth, are faithfully continuing their mission. It is a reminder that when humanity builds something with purpose, it can outlast generations. Voyager does not just belong to the 1970s, it belongs to us today, and it will belong to those who come after. The golden records aboard each probe are the most poetic part of this endurance. They will last far longer than the spacecraft themselves. Gold does not corrode easily, and the records may survive for billions of years, long after Earth has changed beyond recognition, long after mountains have eroded, rivers have shifted, and even continents have broken apart. The Voyagers will still be carrying those discs, engraved with humanity's self-portrait. Perhaps they will never be found, drifting endlessly through the galactic dark, but that possibility does not diminish their meaning. In fact, it strengthens it, because the records were never really about others. They were about us, a message of who we were, carved into permanence, sent out as a promise that we existed and we cared enough to say so. There is something humbling in realizing that the most enduring monuments of humanity may not be our skyscrapers or our cities, but two tiny spacecraft drifting far from home. They are quiet ambassadors of our species. They do not conquer, they do not consume, they do not destroy. They simply travel, bearing witness to the infinite night. In them, we see a gentler side of humanity, the side that is curious, imaginative, and hopeful. And yet Voyager is also a mirror. It reflects our fragility as much as our strength. In the pale blue dot image, we saw Earth as a fraction of a pixel. That photograph has been called one of the most profound in human history, and with good reason. It stripped away our illusions of grandeur. It reminded us that all of human history, all of our conflicts and achievements, have taken place on a single small sphere in a vast sea. Voyager, in turning its camera back on us, forced us to confront our place in the cosmos. It was not just a scientific act, it was a deeply philosophical one. The end of the Voyager mission is inevitable. Every year, the spacecraft lose more power. Instruments are shut down to conserve what little remains. One day, the faint signal will stop, and Earth will listen into the silence, realizing that a chapter has closed. But even when the spacecraft are no longer speaking, they will not be gone. Their trajectory will carry them forward for eons. They will orbit the galaxy, perhaps passing near other stars. In a sense, Voyager is humanity's first interstellar journey, and it will not end with silence. It will continue forever. Future generations will build new probes, faster and smarter. Perhaps we will send sails pushed by sunlight or lasers. Perhaps we will design machines powered by fusion, capable of reaching nearby stars within a human lifetime. But no matter what comes, Voyager will remain the first, the trailblazer, the one that showed us it could be done. Every interstellar mission in the future will be compared to Voyager, and every achievement will owe something to the path it carved. There is also a kind of poetic justice in how small Voyager is. Unlike rockets or rovers, unlike the grand space stations that circle Earth, Voyager does not dazzle with size or complexity. It is, in its way, modest. And maybe that is why it resonates so much. It shows us that greatness is not always about scale. Sometimes greatness is about persistence, about daring, about the courage to attempt something that seems impossible. Voyager reminds us that human beings, though small, can reach for the stars. When the signal finally fades, perhaps we will feel a pang of loss, but we should also feel pride. Voyager was more than a mission. It was a statement of intent that humanity will not remain on Earth forever, that we are explorers by nature, and that even in the face of vastness, we will not stop asking questions. Voyager embodies the best of us. It is our curiosity, our imagination, our humility, and our hope. And so, as Voyager drifts on, silent or speaking, it carries us with it. It carries our voices, our music, our greetings. It carries our science, our art, our wonder. It carries a small planet's story into the galactic ocean. And maybe that is the truest legacy of all, that long after we are gone, something of us will remain, still voyaging, still reaching, still seeking. Voyager's name was well chosen. It is not just a spacecraft. It is a symbol. It is a reminder that humanity's journey is not confined to Earth, nor even to the solar system. Our journey is endless, and Voyager, two tiny emissaries of a blue planet, are already showing the way.